Hello there, everybody. How you doing? Welcome to SkyTour LiveStream. I'm just jumping right into things here, as you can see. So we're cool here. Let me just make sure that we are good. All right, here we are. I wanted to also welcome Daryl Mason to the broadcast. Hello, Daryl. How you doing?
Oh, Mark, I'm well. Hello, everybody.
That's good. And I saw something. Hey there, Kid Sinza. I haven't seen you around here before. Nice to see you. We have Eric McGrath. That's a new face. How you doing in Wisconsin there? It's probably chilly out there. The person that owns the land we're on lives in Wisconsin. And I want to say hello to Greg O'Brien, who was the first one here. And he apparently needs tires. Cosmic Ray is next in line. Cyclone is here. How you guys doing? And Cindy Murphy is here. Nice to see you as well. And we have Donald Kunzer is with us. And Izabela Melamed is here with us. And who else is here? Daisy and Zoe Amethyst. Good to see you guys as well. And I think we'll have a fun night tonight. Clouds are clearing up out there. I think I said hi to you, Donald Kunzer. And then and the new faces, which is great. It's cool to see you guys here. Anahata 77 is with us. That's Bonnie, who lives a few hours from you, Daryl.
Yeah, that's probably 5 or 6 hours from me.
And so that's still in
beautiful
Colorado.
Country down there, though.
Still in Colorado.
Well, yeah, she's way down in southwest Colorado.
Wow.
It's beautiful country down there, but it's quite a distance from me. Colorado's a pretty big state.
It is. Hello, Sam S. How are you? I've seen you the other night. Nice to see you back. Hope you enjoy tonight. We're going to be zipping around the night sky. We have a few clouds that we're messing with, trying to get rid of, but we'll, we blowing real hard, in the air. Make sure they go away. And let's see. All right, so I also have some help in with the people that run the camera, or own the camera, actually. Well, I own the camera, but the people that made the camera, because they're trying to get some support on the diagonal streaks we see in our vision. I sent them samples. And so hopefully we'll get answers as to what's causing it and how it's going to get fixed. Okay, so let's see. We don't want that status. I'm going to go down and just add a couple of factors in here. Just a minute. Still setting up. I'm setting the rates of correcting for our guiding system here. That's all. All right, that's good. And then I'm going to turn off one of the other elements.
I see a globular cluster.
Yes, you do. That was my target object.
Hope so.
Okay, and now
what are we looking at?
I believe that's measure 2, but I'll have to go look and see.
Okay.
Let's get it up into the view a little more, though. You know what, folks? One of the things that I just find amazing is this is live. This is live to my broadcast system that's 2,500 miles away from the telescope. But either way, it's all live to your eyes. And I think that's... I don't know, I never got over that, how interesting that is. It's just neat that it's so happening right now as we speak. We're seeing these beautiful objects right now. We can zoom in on these things, right? Like this. And we're going to focus too, and that's why I'm zooming in, so we can see that the focus is a little soft here. We'll fix that. But we can actually bring it down here, and you could just run it through the whole gamut of exposure. You can see it's a little out of focus, which is good. That's what we want. So we'll actually connect our focuser now.
I saw something interesting today about globular clusters. Anton Petrov has a new video out. He releases a new one about every day. But he talks about the Andromeda Galaxy, Messier 31. And he says, among other things in the vid, the Milky Way has about 150 globulars, and Andromeda has 450 or more, like 3 times as many. And that and other things he talks about in the video makes some people think that Andromeda Galaxy has absorbed or merged with a lot of galaxies.
I understand that thinking. I mean, it has over 1 trillion stars in it. And it's possible that it's absorbed some galaxies, but they would probably have to be smaller. You know, because Andromeda would otherwise have a morphology that's really strange looking to us. It might even be diffuse or a full elliptical if it collided with several galaxies that were more like...
he says it may have collided with a bunch. He shows a star map of the area, and there are a ton of little satellite galaxies around 31. And he said, too, which I had heard before but forgot, that evidently there are 2 cores inside Andromeda in the nucleus, and they think that there's 2 supermassive black holes in there.
Which would imply a merge.
Yeah. And he mentioned that the biggest globular cluster known is in Andromeda, and it has a name. I don't know if we could find it or not if you entered it. I think it's called Mayall-1, Mayall-1.
Yeah, what's that? I don't know if we have that catalog, but if we just have a image of where it is, we can probably find it.
Yeah.
I mean, okay, we're focused now, so if we zoom in again now, we should see some stars. Oh yeah, look at that. Now we see sharp little pointy stars. No, they're not sharp because we're looking at 1 second exposures. If we just do, say, 12 seconds on this, all right, and we'll get out of this and go right into a live stack. It's also a test to see, for me, what the quality of the night is. Okay. Let's adjust. Okay, so that's what it's looking like, right? That's all the data. So what we're going to do is now we're going to cut out some of the data that we don't want to see. Put some black into the sky there. Now watching this next stack occurs, you'll see some more of that noise go away. Right, so now we can bring it down. Look at that. So we can bring it right down to almost nothing. But it's still overexposed in the center. A 12-second exposure. Not bad for a faint globular cluster you can't see without a telescope. Okay, this, I believe, is, I think it's, is it Measure 2? Or no, it's not. This is that Measure 2? Yeah, Measure 2.
It says.
Yep, that's right. And, while we're at it, okay, so there's that globular cluster. Let's look at it into full frame size. Okay, this is the full frame size. That's how big it is on our frame. Okay. Alright. And you know what? We'll be saving this anyway. So, because stars you can save pretty much after, like, you know, 5 stacks. You don't need to go crazy with them. But we can pull this back a little bit so you can see.
I like globulars.
And globulars are pretty. All right.
They're all different. They kind of have each their own character.
They do. They have their own strange idiosyncratic objects in them sometimes. Patterns of stars. That's cool. All right, so this guy then is not the obtuse nebula, which is my dang nebula. That's just me saying that. Haha. Okay. So we'll get rid of that. It's actually measure 2. And it's a globular cluster. Alright. And so that's what that is right there. There we go. Throw that out there for you. And this is M2 up here. We're going to change it to M2-GC for globular cluster. Okay. Alright. So that's all we need for this guy. We only need, we're going to do 14 and be done. There we go. Now we'll save it, and then we'll save it exactly as seen. Okay. Then we'll hop out of here and go back to our ready-made night vision view.
Globular vary in size a lot. Some might have 50,000 stars. The biggest one in the Milky Way is Omega Centauri, I've talked about before. It has like 4 million stars in it.
Yeah.
And it's huge. Evidently, that L1 in Andromeda is several times the size of Omega Centauri.
Wow.
Which helps make people think that it's an X-galactic nucleus.
Mm-hmm. Hello, Claudio Ramos from Chile, and John G. How are you? This is measure 2. Okay. One last moment. I'll throw that out there for you. Measure 2, a globular cluster. We just finished exposing it and saving it, so it'll be up on the site, the free site, M2GC, globular cluster, in just a little bit. As usual, Ray is offering some awesome facts about measure 2. Yeah. Maybe Ray will like this too. I went into the back room here at the astronomy bunker, and I dug out my AAVSO atlas with every single variable star known at the time of that printing, the American Atlas of Variable Star Observers. Something, I think that's what it means. And we used variable stars, and we were looking for stars as well. In fact, we had to kind of make sure we didn't have variable stars when we were doing some of our tasks, because they could throw off things we're trying to find. Let me just move this over a little bit. Alright, here we go. Just a sec. Little adjustment. Here we are. Okay.
Variable stars are cool.
Yeah, they are.
Some are more than others. The star Algol in Perseus.
Famous one.
It is I guess the most famous one.
Yes, it is.
Algol means the ghoul or the demon.
Yes.
And Algol represents the head of the Medusa, the Gorgon.
Mm-hmm.
In the Legend of Perseus and Andromeda, where he cut her. You know, she had a head full of snakes for hair, and it turned to stone if you looked at her, and he cut her head off and used it against the monster to save Andromeda.
Mm-hmm.
It's an eclipsing variable. That is, it's, I think, a double star, a multiple star system, and one star passes in front of the star and partially eclipses it, hence eclipsing variable.
Mm-hmm.
And its brightness changes on a regular basis. And the ancients noticed this. You know, they were pretty acute observers back in the day, even without telescopes.
Mm-hmm.
And they noticed that it changed brightness on a regular basis, and that's where it earned its name, the ghoul.
Mm. That's fascinating stuff. All right, I'm going to... this is now measure 15, another globular cluster that we've seen before.
Oh boy.
Yeah, and we'll check this out. And I'll just make an adjustment for the name. There we go. Oops, I said the wrong thing. Okay. All right, and now let's go up and make sure that we're guiding properly, and I'm going to be sure we will in just a second. When I come in here, I'm going to guess that we're going to see that we're already guiding. There goes a Starlink satellite. Enter guide mode. You can see we're already guiding. Okay. And it looks like we're stable. So let's do a 12-second shot on this as well. Keep it the same. And we'll get rid of this right here. And we'll live stack it and clear the last stack. Now look at that. All right. And look at this next one. See a size difference. See that? When Daryl said that each one's a little bit different, the last one took up about this much space. Well, a little bit less, a little bit about like this much space. And this one took up less space than that.
Yeah.
So
it may be a little more concentrated in the middle than M2 was.
Yeah, and we could figure that out by doing this and then working it down. So let's work it down. Okay, so this is about where we'd want to see that. Very nice.
Uh-huh. I'm sure when we look at globulars, they'll benefit from more focal length when Marc gets the new telescope.
Yeah.
Get a nice close-up view of them. And they are all really different. Some have little features inside you can see, like the propeller in Messier 13, and the vertical line of bright stars in Messier 4. And each one has something a little different to offer. This one has what looks like a line of stars running left to right down at about 7 or 8 o'clock.
Yeah. Cosmic Ray, he writes, hit the thumbs up, folks, each time Marc gets a new tooth. I missed something?
I wish I had got a new tooth every time.
Well, I don't want my mouth to be covered with,
I've got one tooth left, and I got to take care of it.
Cyclone says, will this be a nuclei of an old galaxy? Not in our present way of thinking, Cyclone. We don't think that globular clusters are old galaxies. But they are mysterious. They're very, very old. They're among the oldest things that we see in the universe. And that means that the stars are all very, very old inside those clusters, which means that they don't have a lot of elements other than hydrogen and helium in their atmospheres of the stars. The stars make up the chemical composition is mostly hydrogen and helium. Stars like the sun have a veritable smorgasbord of elements that it was made with, because there were already those elements in the solar nebula when the sun was made. But for these stars here, these are called population 2 stars. And these population 2 stars have very few elements other than hydrogen and helium. Because they're so old, those elements had yet to be synthesized in the cores of bigger stars when these clusters were made. So that means that in all likelihood, unless these objects picked up stars that were heavier in these objects beyond hydrogen and helium, and we call those collectively metals, even though they're not all metal, then these clusters will have very few planets around them in their star elements. There won't be very many planets around them. But these are what are called halo objects. They are in the outer halo of the galaxy, and they orbit the galaxy. So in some cases, they will plunge through the disk of the galaxy, go down and plunge back up through the disk of the galaxy. Now, when they do that, it's possible that they shed stars or gain stars. And in the time the galaxy has been here, the globular clusters do offer us some strange anomalies. But they don't offer us enough to show us that this process is happening all the time, but we do see some strange things in some globular clusters. But frankly, you're looking at the most ancient objects in the universe, pretty much, when you look at globular clusters in our galaxy.
Some think that they may be the remainders of ancient galaxies. Petrov talks about that in his Andromeda video.
Well, I just finished saying why I didn't think that was the case. Okay.
No, I just finished saying why they are. Or maybe.
Okay. We can agree to disagree. But,
yeah.
It's fine.
I mean, you have to think, if these are about some of the oldest things in the universe, that, well, if they're cooking way back when, they would have been like the seeds that drew everything else to them. Would have become galaxies.
I can see the thinking, but what I don't understand is the galaxies the galaxy as we see it, our galaxy with its spiral arms, other galaxies, we see globular clusters in every galaxy. And if they were all the remains of previous galaxies that were once absorbed by those galaxies, they had to have some mass. And that mass would undoubtedly do things to those galaxies that would leave clues as to what happened. As in the Whirlpool galaxy, it has this long tail of material that's spinning out from this galactic collision. Because technically, if the inside of that second little galaxy in the Whirlpool is one of those such galaxies that would then be a globular cluster someday, then let's suppose we look forward in the future and they orbit each other, and finally all that's left is a little tiny globular cluster, right? What about all the gas that was ejected from the galaxy? We should see that in radio studies around galaxies. And there are radio halos in some galaxies and jets in others, but nothing that indicates that 150 globular clusters used to be galaxies. This region of the universe would be a veritable mess of neutral hydrogen and other elements that were stripped away during this merging process, and we just don't see it. And
if they're that old, they could have lost all their gas.
Well, the stars are very old. They're extremely old stars. So they're saying, I mean, in my view, these are extremely old objects.
Yes.
And I don't believe they're galactic cores. I think that the mystery that we have yet to solve is how they formed. But I don't think they formed by them being the cores of all these massive galaxies that collided with each other and left a singular galaxy behind. If that was the case, the Milky Way would have more than one supermassive black hole, because one of them would have merged eventually with ours and would have drawn many stars with it. So in that case, the galaxy would have become a mishmash. It wouldn't be a very neat spiral. It would end up being a mess, more like what we call a diffuse galaxy. I'm sorry, an irregular galaxy. And I don't think that the globulars satisfy that quality, that capability, and that characteristic that we're looking for. I just don't. But that's me. That's me. So, Anton Petrov, he does great videos, but he's not an astronomer. I mean, and that doesn't mean anything. But what I'm getting at is, I think that there's a lot of research left to be done, but it's not Anton Petrov that's doing it. It's these other guys that are doing it, and those are the guys you should read as well. I think that he's wonderful and has some really, really good stuff. I just don't agree with him on this.
Okie dokie.
Okay, whatever. All right, so this is Measure 15, and we've had enough on this one. We'll save it, and save it exactly as seen. And then we'll get rid of our stack.
When you look at the Messier list in order, there seem to be quite a few of the earlier objects are globulars.
Mm-hmm.
2, 3, 4, 5.
Well, this is 15 too, yeah.
Ray, can you rephrase that? Cygnus, I mean, when we look towards Cygnus, we're looking over at the next spiral arm over from us. The constellation itself, I mean, it's just up there in the sky. Most of the cool stuff we see is a couple thousand light years away, though.
Oh, yeah. Ray says Mesh 15 contains P's 1, which is the first planetary nebula discovered within a globular cluster. And as you can imagine, these stars would be very old, and when they do die, they will, in some cases, expand into red giants and then shrink into white dwarfs, leaving behind a planetary nebula. And I mentioned before that several of them exhibit characteristics that are odd, and this is one of them. You know, that this one has a planetary nebula within it. We can't see it because it would require a massive amount of focal length to see, actually. And I think we'd have to see it in the radio spectrum. I'm not sure. I don't think I've seen visual spectrum images of it. I haven't, but they may be out there.
What I would assume, as old as globulars are, they must not be terribly big stars.
Right.
I assume they formed all at about the same time as clusters tend to do. What stellar classifications could you say are common for globular clusters, considering that they're so old?
Well, I mean, you can have any stellar type, you know, anywhere along the spectrum, but depending on what was around at the time, I think we're talking about stars that might be anywhere from A to K. You don't have M stars in them because, for whatever reason, that's true. And you don't have O stars in them, but you might have what's in between, probably not Bs, because you need an awful lot of mass to make O and B stars, and they're really difficult environments. So I would have to say, and I'm just guessing, but it's probably A to K type stars. But again, they're population 1 stars, so all they have is hydrogen and helium. Now, depending on what they're
population 2.
That's what I meant. Sorry, population 2, and just because we don't have a spectrum of the clusters, if we did, we could look at their hydrogen lines, and depending on how broad their hydrogen lines are, that can help us classify their spectra. So I'm not sure.
I always thought it odd that the older stars are called Pop 2, and you'd think they'd be Pop 1.
Yeah, I know. We make that mistake often, you know, because population 2, I guess, is like the term refers to the older stars, of course, obviously, and I don't know why it was population 2, and that's probably more of a convention than a fact-based thing, just convention. And Marcin Johansson, hi there, how are you? Marco, hi, good to see you.
I would guess that back when they first started serious study of globular clusters, and they noted, you know, the poor metallicity of the cluster members.
Yes.
Was probably different than the run-of-the-mill stars we see up in the sky.
Yeah.
That, you know, are more metal rich, and therefore they called them Pop 2. But it just turns out that they're the older ones.
Yeah. You know what? I'd like to... What's the name of that? What is that globular cluster in Andromeda? Do you have any idea where that's located? Let me see what catalog we're using, because...
Mayall, Mayall1, I believe.
We may not have it in here, but I'm going to look.
Let me look it up.
We have Mela. Okay, well, I'll turn on these others anyway. It might be known as something else, too.
excuse me, Mayall 2.
All right.
Also known as NGC 224-G1.
That's what I wanted to hear. NGC 224?
NGC-224-G1. And my
Okay,
bad,
it's
it's Mayall 2.
All right, it's not in here as that. So let's look at, it's Mayall and come on. What's going on here? It's typing in S when I'm typing in A. Mayall.
Mayall 2 is, that's Roman numeral 2.
Mm-hmm.
Considered to have twice the mass of Omega Centauri.
Okay.
May contain a central intermediate mass black hole.
Let's find out where. Okay, so Mayall's object is something below the horizon. It's not this. All right, so it's not hidden here. But do you have a? Is there a way to get a finder chart for it so we can actually go look for it?
I'll give you right ascension declination.
Well, that would be very helpful.
Okay, 0 hours.
Oh, just a minute. Okay. Let's go put that in up here, folks. 0 hours.
32 minutes.
32.
46.51 seconds.
Okay. All right. And
Declination when you're ready.
I'm ready.
Plus 39.
39.
34 minutes.
Okay.
39.7 seconds.
Okay. All right. And now we're going to just say go to. And so it should go there. There we go. So it's heading somewhere. Let's go find out. That's about right.
Say it's about 130,000 light years from the nucleus of M31.
Okay, well, it didn't quite go the right place, did it? Let's make sure. Alright, we gotta make sure that was the right spot, yeah?
Mayall's object picked up on that.
Yeah. But the right ascension declination that we're looking at doesn't show it here. I mean, look where it's showing us. It's showing us near the Andromeda Galaxy, but not within the Andromeda Galaxy. We're like several degrees away. See that?
Yeah.
Well, is it possible that... Hey, that's too far away, as far as I think. So, I'm guessing that we're not going to be able to see that. Well, while we're here, we might as well try to look at the Andromeda Galaxy and see how it looks. I'm glad we got I didn't know if we're going to have a clear sky tonight or not. It was close. Okay, we'll go here. Alright, and then we're going to go here. Alright, and now you'll see the Andromeda Galaxy sliding in from the left. Here it is. Well, it was a good try. I wasn't sure that we would actually be able to see it. I'd actually have to see a finder chart to see where it is. And not only that, I'm going to take a moment to just set up and make sure that my coordinate systems are correct right now. Alright, so here we go. I'm going to head a little west right now. Got to do this way. I'll be right back at you folks. Just a sec. Cyclone's asking what the most distant cluster is. Okay, let me do this here. All right, there we go. We're in the center of the Andromeda Galaxy. Let's go here now and...
For what we were saying earlier,
Yeah.
because of the widespread distribution of metallicity indicating multiple star generations and a large stellar creation period, many contend that it is not a true globular cluster, but is actually the galactic core that remains of a dwarf galaxy consumed by Andromeda.
You're talking about Male's object? Male's?
Yep.
Okay. So Male's object or Male 2?
Male 2.
Okay. Okay, well in that case it might be. If it's that much bigger than Omega Centauri, I could see how that could be possible. Okay, we are at 04359, 04354.
Male's object.
Okay, we're good here. All right.
That's what Stellarium showed you as Male's object, right?
Yes, down below the horizon.
Okay. Yeah.
Oh, I started the wrong. Okay.
Male's object is an Ursa Major,
Okay.
result of two colliding galaxies located 500 million light years away.
All right.
Interesting pic of it in its article.
Okay, let's do this now.
One galaxy hit another one right in the middle,
Mm-hmm.
right in the bullseye.
All right, we're going to try a 45-second exposure here. We've been guiding successfully here for a bit. And we'll get out of this and go into our stack. And clear our stack from the past measure 15. Here we go.
Male's object, ring-shaped galaxy with a tail emerging from it. Such collision between the two galaxies created a shock wave that initially drew matter into the center, which then formed the ring, also known as Arc 148.
Mm-hmm.
It's a nice Hubble image of it. 500 million light years away. I mean, we wouldn't see much, probably.
Yeah. Okay, this is looking really interesting now. Okay, there's that beautiful OB association down here. Young hot O and B stars, another one over here. There's some throughout this spiral arm here. This satellite going through, as we get more images, it'll be overloaded with the blackness of space behind or the colors of the galaxy. Here's a beautiful nebula collection. This is a real concentration of hydrogen gas here in the galaxy. I mean, it's all concentration of gas here. But this is pretty, man. This is nice. 45 seconds is handling it just fine right now. Look at that. That's good, pretty good. Oh, yeah.
John, we've seen colliding galaxies before.
Antennae.
Yep.
Yeah.
It's in the spring sky.
Yeah, we're looking at at changing this camera to a better camera that's going to give us a better ability to zoom in and see things. So we may not need more focal length per se. We might be able to zoom way in with real nice clarity. We just need smaller pixels on our camera sensor, and that's what we're aiming for. This camera we're using is really a beautiful one, though. Yeah, go ahead.
Yeah. Marcin, if I understand your question, the change of metallicity in stars over time comes from succeeding generations of stars. Early stars start out metal poor. When they die, they release heavier elements which fall into the new stars being formed, and it tends to build the metallicity over time, succeeding generations of stars.
That is absolutely true. The thing that's interesting is that the universe is basically a element builder. Stars are element builders, and they build all these elements in their cores. And when they go supernova, the next generation of stars, as Daryl says, are made from those, which have all that stuff in it. So the only place where a star is doing fusing anything into anything, is right in the very core. All the rest of that outer envelope is just plasma. It's superheated nuclei of other atoms that can't even form atoms, okay, because it's too hot. All right, so the electrons are loose, the protons are loose, and the protons and electrons stream toward us as solar wind. See, so that process is one that wow, it's beautiful. That process is one that is the one that will take those elements in the outer atmosphere of that star and just churn them around for billions of years, not doing anything with them. And so when the star does die and it goes into a red giant phase and starts expanding and contracting, those outer layers just slough off for a star like the sun, and they puff off the outer layers, which contain all those materials it was made with. And the biggest stars, when they blow up, all that stuff goes as well as the core, where all these new elements are made, right up to iron, which is kind of interesting. Iron 56, I believe, isotope. So it's pretty cool. This is nice, Daryl.
I've wondered too, again, per the guy's videos, when he talks about two supermassive black holes, he shows an image of it, the nucleus of M31, and that might be contributing to why the nucleus is such an oval shape.
Mm-hmm.
There is separation between them.
Let's try adding an enhancer now to give us more detail. Let's take a look at what this looks like after I enhance. Ready? Here we go. It's on. That brightens a lot, which is overblown, but then you see this much clearer. Let's zoom in on that section. That's a pretty section right there. That's a really pretty area. Look at that. Here's that nebula I was telling you about last time. This is Messier 32, elliptical galaxy, which is a companion to Messier 31. And as we keep cruising up Messier 31, besides the bright core, we also see more nebulae, more blue stars being formed in the spiral arm that are now here. Look at that beautiful arc right there. Look at this nebula. Wow, there's a loop in there. Look at that, Daryl. Let's zoom in on that. You can actually see this little loop in here. It's got a loop in this. That's interesting. Let's find out if we can just get a little more detail out of it. A little more contrast, maybe. Tiny bit more contrast. That looks good. Wow. I like peering at a distant galaxy like this. This is pretty cool. Very neat. Yeah. Wow. So, you know, when you look at this, you know, that nebula right there might not even be there anymore. Well, it probably is, but it might look different now at this very instant, because you're looking at it as it was 2.57 million years ago, because that's how far away the Andromeda Galaxy is, 2.57 million light years. And light's the fastest thing in the universe, and it takes 2.57 million years for it to get here from there. So that's pretty cool. That's just amazing. And the Triangulum Galaxy next to it is 2.7 million light years away. But they're actually locally close to each other in space. And it's possible that they've interacted in some way. That's just nice. So let's go back down here. We've stacked 12 of these already. That's pretty good.
When you see those blue areas there, OB associations and such, those are the product of the H2 regions, the red areas, which don't show up terribly well, and the making of the stars that turn into the OB associations.
Yeah.
OB associations being very large, bright, hot stars.
Yeah, type O and type B stars. Remember the OBAF GKM spectral classification that we talk about? The O and the B stars are the hottest there are. O are much hotter. Much of their radiation will be in the ultraviolet, which is why you don't want to be near a star that's 1 million times as luminous and it puts out 1 million times the energy actually of our sun. That would be a rather instant death sentence. I don't even know if you'd know you were dead. Hello, Sean Farva. Thank you. That's very kind. Okay. I guess we have to accept that, Sean. But thank you. Yeah, this is looking good. I'm pleased with how we're guiding tonight. This is good. We don't have a lot of wind. Not at this point. We're actually at a very vulnerable position with a telescope.
I wonder, oh, you just zoomed out. We can't see it.
Where do you want me to go?
Well, there to the upper left, a little bit of the nucleus of the galaxy.
Yeah.
When you were zoomed in, you were just mentioning not that far.
Okay.
A little more. A little more.
Mm-hmm.
Okay, right there near the left edge, there's two bright stars up toward the upper left.
These?
Yes, the lower one in particular, that must be a multiple star.
It is.
You see how notably oblong it is compared to the round stars of all the others.
Yeah, I think we can actually separate that too if I do this. I think we see darkness in there, yeah? Those are two separate objects, no?
Okay. John G., how would the components of a star change to have increased metallicity if it has to start at hydrogen? Time, fusion.
Nucleosynthesis in particular.
Yes. The star builds heavier elements by fusion or nucleosynthesis, as Marc said, over time. Again, the first stars, all they had were hydrogen and helium. But as they got older, they start fusing heavier elements. And to astrophysicists or whoever, astronomers, people that look at really old stars, as Marc referred to earlier, they call anything heavier than helium a metal, even though it's not a metal, strictly speaking, as we understand it.
Yeah.
But as the star ages, it builds successively heavier elements, and thus it increases its metallicity. Ultimately, the star dies, either becomes a planetary nebula or like a supernova, and releases the heavier elements back out into space, where they help form later generations of more metal-rich stars.
Yeah. We've talked about, on SkyTour Radio, we've talked about the whole nucleosynthesis process, and the bottom line, it's really simple to think of it this way. The most abundant element in the universe is hydrogen, and the second most abundant is helium. Next is oxygen, followed by carbon. Okay? So, for one thing, it stands to reason that carbon-based life, such as us, would tend to be the rule in the universe, not silicon or anything else, because silicon couldn't support that, actually. Couldn't support the variation of bonds required to make a life form that's flexible and sustainable. But once you start fusing hydrogen into helium, it's a very complex process, okay? It's not just hydrogen goes to helium. Everything we talk about is an isotope. An isotope, that is to say, a different variation of the same atom. So you add a neutron to a hydrogen atom, it becomes another type of hydrogen atom called deuterium. And deuterium is what eventually is made in a star that forms an isotope of helium. Okay, those isotopes then can decay and go to something else. Now there's a process that happens in stars, just like the sun even. You know, we've always thought, you know, in terms of astronomy, you know, you're taught that a star makes a big heavy star makes elements up to iron, which is number 26 in the periodic table. And then, you know, they can't make any more because iron takes more energy in than it gives out. So it's a no-sum game for, you know, to go beyond iron. So you can't fuse anything past iron. Yet we have elements that are way past iron. Now, how does that happen? And do only massive stars make elements past iron? Well, the answer is no. As it turns out, stars like the sun can make elements heavier than iron, but it's a process called neutron capture. It's also known formally, and you can look this up if you want, the S process, the letter S dash process. And the slow process is how stars like the sun, massive stars, and other stars produce more elements that we see in the populated in the periodic table over time. And as Daryl said, it does take time. There's a lot of time that elapses, especially when the slow process is involved. And that's why it's called the slow process. In a supernova, a different process takes over to make elements that are heavier than iron faster. And as you could imagine, that's called the fast process, or the R process. So these two processes are the way that elements further in the table are made. And other than the typical tracks within the core of a star. You know, helium makes nitrogen, carbon, oxygen, fluorine, magnesium, up to iron, okay, and nickel. And when a star starts making iron and nickel, interesting thing, when a star is making elements, we can tell by the way the star is producing elements from its evolution. We can tell that the star may be, say, 1 day from a supernova, because there's certain processes when silicon is being made in the heart of a star. That process happens for like 1 day, and then after that, you're going to get a burst of neutrinos from that star, and that's the herald of the core collapse, which then takes over, and boom, the star blows up. So that's really interesting, and that becomes a type 1 supernova, where it's a core collapse supernova. So it's really cool. There's various kinds of supernovae as well. And there's even novae, okay, just a nova, not a supernova. A supernova destroys a star. A nova is a recurring brightening, which occurs as well, but you have to have a binary star system for that to occur. Kind of like what's called a type 1a supernova, where you have a star with a white dwarf around it. So the same kind of thing, but the white dwarf in a nova isn't destroyed by the fact that it gained too much mass. It actually fuses it off and suddenly makes a brightening, and then once it's done, it goes back to just being a white dwarf again for however long.
30 or 40 years ago, back in the days of Carl Sagan's original Cosmos,
My favorite astronomer.
yeah, they used to think that the heavy elements came during supernovas, stuff like gold, and all the natural heavy elements up to 92 on the periodic table.
Yeah.
Nowadays, it's fashionable. They think that the heavy elements are made like when neutron star mergers happen and stuff like that. The sort of thing that we see nowadays with the gravity wave telescopes.
Mm-hmm. Yeah, I mean, we're learning a lot about the universe. Certainly, when I was learning my astronomy, it was a certain level set of information we had. But since then, and even in graduate school, I had to keep up with everything going on in astronomy because it was a very fast-moving field. And it goes like this. It goes really fast, then it stops for a while. Then it goes really fast again. We're in a period right now where it's going really fast again. And that's all because of one new development. Does anybody know what that was? One development that just occurred.
The gravity wave telescopes, LIGO and Virgo?
No, not the LIGO systems. Those are the gravity wave detections. Those are very important. The Event Horizon Telescope is also very important. But no, yes, Genghis got it. And so did Marson. Yeah, very good. The James Webb Space Telescope. It's allowed us to see galaxies that are speeding away so fast that their light is so far into the infrared we've never ever seen them in all of human history until now. That's correct. But as Daryl just pointed out, those the LIGO detectors, the Laser Interferometric Gravitational Wave Observatories, the what? The telescopes, basically the systems that detected gravitational waves, those were a major breakthrough as well, and that's part of the fast-moving world of astronomy now as well. And then beyond that, we have what's called the Event Horizon Telescope, which is a consortium of radio telescopes all over the Earth. All right, and Earth is an 8,000-mile diameter. So that 8,000-mile diameter, thank you, Sean, that 8,000-mile diameter with telescopes dotting all over it, as it rotates around, we're getting effectively an 8,000-mile diameter crude but effective telescope. And that gives us the resolution to see things like the black hole in Messier 87, which is like 55 million light years away, and the black hole in the center of our galaxy, which is called the Sagittarius A, or Sagittarius A star. Well, it's not really a star, it's a point source. So, as you can see, these things are taking us and propelling us very, very quickly into a whole new level of understanding of the universe. So when we look at the Andromeda Galaxy, we can just imagine what we're seeing here. We can just imagine how that galaxy looks through the eyes of the James Webb Telescope. You know, and then we have the Atacama large submillimeter array down in Chile, showing us things that we've never ever known were there until these telescope arrays were put online. And that just looks like a row of basically half plates in a long field. It doesn't look like a telescope at all traditionally, but it is. And as the Earth rotates, it goes through space, and this thing is just peering upward the whole time. And every night, over and over, they can get data. So astronomy is also a patient sport, if you will. Well, I'm going to take off the enhancement for a moment. See the
Martian.
There we go. Let's look at the.
Sorry.
No, it's okay. I'm going to look at the dust in this galaxy. You can see
Martian,
a couple spots.
I dare say they don't have to pay for telescope time on the web, but you have to have a really good proposal to get your name on the list. You know, it's like the old saying, if you have to ask, you can't afford it. But then Martian expands his question to a question for you, Mark.
Oh, he does? Okay, let's see.
Have you ever dealt with scheduling telescope time for a research project? If so, what was it like?
Oh gosh, that's a nightmare. Let me let me explain. When you have one telescope on a mountain, you want that you covet that telescope. You'll hide out in that telescope to get time in between everybody else's time. All right, and when I was working on the parallax program, luckily for us, we had slots of time that were devoted specifically to the parallax program. So I was there midnight to dawn every single night through the winter, 10 below zero in that dome. You couldn't have it warm. It had to be the same temperature as the outside air. And the purpose was so that we could get the parallax data for our program. And what's parallax data? Parallax data is basically the distance to the nearest stars. And what we're doing is this. If you consider the Earth's orbit is like this, if you look at me over here, okay, the Earth's orbit, say this distance, right? And when we're on this side of the Earth's orbit, we take a picture of the distant stars and a nearby star. And on this side of the Earth's orbit, we do the same thing. And we see the parallax, the difference between the angle of that closer star to the farther ones. How's that work? Very simple. You put your finger out like this, and you close one eye, and put that finger against something you know on the wall. And then shut that eye and open the other one. And you'll see that it changes position. Your finger changes position against the object of the more distant wall. That's parallax. And we use that. We can use that shift in position of the star based on the size of the Earth's orbit, okay, to determine the distance to that star. It's called the parallax angle. All right, and that parallax is interesting to talk about, and it's good out to about 300 light years. But with better systems, we can get out to almost double that now in parallax. So it's actually a pretty good system for determining the nearby stellar neighborhood distance in 3D and setting it up in 3D.
Yep. When you hear the term parsec, that means parallax arc second.
Yep.
And a parsec is 3.26 light years.
Yep.
And at 3.26 light years, Earth's orbit around the sun will subtend 1 arc second. And that's what a parallax arc second is. Right.
The star that's 3.26 light years away will move 1 arc second based on the size of the Earth's orbit. And that's what Daryl's saying. So the bottom line is that would tell us exactly what we would want to know about the star. We'd know its distance, and we use that. We use that a lot. In fact, that process was started, back in the 1800s, I believe. And they used a lot of times they used Alvin Clark refractors to do the measurements, and we did that too. I had to put these large gratings over the end of the telescope objective, and they're slotted gratings. And you say, well, what do you do that for? Because they would make crosshairs. And you would actually measure the tip of the crosshair to the tip of the crosshair, tip to tip. And that would tell you the exact geometric position of the star in the middle. And so you didn't, because remember, a star's image is bloated, so what's the center of that? Well, with those gratings on there, those crosshairs would actually draw lines right to that geometric center. And that's how we would measure the position of a star with accuracy. In fact, our data, we shipped all the way, I shipped our data to Yale University because they had what's called a measuring engine. And they would go through and do an extremely precise measurement with their supercomputers to give us those actual positions. And then those positions would be used to determine how far the star moves the next time we took a picture of it.
Yeah, Uberku says, am I understanding that correctly? So with parallaxing, you're measuring a single object from two remote sources, then comparing the different measurements over time. Yeah, you're measuring them. Traditional parallax would be done 6 months apart when the Earth is on opposite sides of its orbit around the Sun. That gives you a baseline of 186 million miles.
Yeah.
And whatever shift you see an object makes against the background sky, that's how you determine its parallax.
Right, and that what we're actually measuring is the position of the star. All right, and then 6 months later, as Daryl says, when the Earth's on the other side of its orbit, the Earth has moved, as Daryl mentioned, 186 million miles, basically. And now we look at that same star again, and you'll notice that it's shifted slightly against the background stars, based on the fact of its closeness. Okay? Now, one of the stars that would move the most is a star called Barnard star. All right? Because it's one of the closest to us, if not the closest, actually. And so that star would shift the most that we would see it. Oh, here we go. Yeah, and so the spam begins, guys. It seems like, what? If you're somebody now, they stream and they spam. I love it. That shows me we're succeeding. Anyway, so that said, that is all good. That's how the parallax system works. If someday you want to go through how to actually calculate parallax, we can do it, because you could do it in everyday life. All right. In fact, rangefinders do this. Okay, the rangefinder cameras do this as well. So really interesting stuff. Parallax is basically the mother or father of modern astronomical position deduction. That's the way to say it, I think. That makes sense. Okay. All right, so we've got a number of exposures here, so we'll pause this now. That's really.
Cruz said something about the James Webb's telescope earlier. I can't find it exactly now. They're already in the planning stages for the successor to the Webb telescope. I've seen a few articles about it. They're supposedly going to call it the Sagan Space Telescope after Carl Sagan.
They should.
It's going to be several times the diameter of the James Webb mirror, and supposedly it's going to be another visual telescope, more like the Hubble than the Webb.
Yeah, I know.
And it'll be a space telescope.
They might actually have an infrared capability, because Hubble can see into the infrared as well.
Yes.
And you're not going to launch a visual telescope into space without launching an infrared telescope. That's.
Well, yeah, but the talk I read was, it's not going to be an exclusive infrared telescope. They called it a visual, and of course it'll have infrared capability somewhere.
Cyclone says, what's the farthest thing in the universe you know about? Aha, that's actually an easy question. That answer is the CMB. What's CMB? The cosmic microwave background. It is the remnant of the Big Bang as seen from here, looking out as far as we can possibly see into the universe. And It's the also known as the 3 degree Kelvin background radiation. And it's not the same in every direction. It's modeled. It has higher and lower temperature throughout. It's not just a constant, screen of temperature. It's got some hotter and cooler areas, which is pretty interesting.
And that is a relatively recent discovery. I mean, it's been a while now, but almost by definition, at one time they thought the cosmic microwave background was steady and constant across the sky and across the universe.
That's right.
But now they found that it's slightly more in some directions than others.
Yeah. Well, it was actually Wilson and Penzias that found it. Robert Wilson, Arno Penzias, they were astronomers. It was actually found, 50 years ago. So that's relatively recently. And what's interesting is they used this their horn antenna, and they were seeing noise in the antenna, and they thought that it was pigeon poop in the opening of the horn. And, so they went and they cleaned it out, and this stuff was still there. What the heck is this stuff? What they were seeing was this new discovery, that there was this noise in every direction they were looking. And that is the CMB, the cosmic microwave background. It's everywhere we look. So it was everywhere, and they thought there was something wrong with their system, and it was not. It has since been, confirmed 1,000 times over with other instruments, so it's pretty cool.
They were working for Bell Labs at the time, weren't they?
Yeah, that's right. Okay. All right, so we have 30 stacked images here of the Andromeda Galaxy. That's a real pretty one. That's going to look pretty when it's processed. Oh, man. And I guess, if it looks that good, we're going to have to also do Measure 33.
Of course.
Of course. I mean, it's nearby. It's nearby in space, So let's back out here. Let's check it out. Yeah, and we'll come down here. Come on. There we go. So you guys having a good time tonight? Farva, thank you.
Farva certainly is.
He is. Thanks, Sean. Hey, Sean, have you started reading the book yet? Okay, let's check out this galaxy here. Let's go, first of all, and let's go to our 1 second here and night vision mode. Oh, and to answer another question, I think Cyclone, you asked this question. You asked what this bright object was here. I think that's what you're talking about. You weren't talking about the nucleus. Okay. There's two bright objects. We've got this one here, and we've got this one here. Sorry, I forgot to answer your question. So obviously this is Measure 31, the Andromeda Galaxy, right? This is Measure 32. It's a companion or satellite galaxy to Andromeda, orbiting Andromeda. And this is Measure 110. This is also an elliptical galaxy that is orbiting Andromeda, and they're all sort of mutually orbiting each other, but Andromeda is the most massive, so it's moving very little compared to these two galaxies. And these satellite galaxies are what are called elliptical galaxies. They've been stripped of all their dust and gas, mostly, and they're just stars, except this Measure 110 actually does have some patches of dust in it, which is really interesting. Now, it could be that Andromeda has stripped these galaxies of all their dust. That's possible. We only see the end result. That's like seeing a car crashed into a pole. Everybody's okay. And you go, well, how do we know how fast he was going? Well, there's clues that people can figure out how fast it was going. Well, where did it come from? Well, there's clues to figure that out too. But you have to go through the process of trying to figure that out. So we have to reverse engineer what happened in this location, for instance. So that's all very interesting. All right, let's go now to Measure 33. We're going to go to Measure 33, Kif. Off we go. All right, Measure 33 is right nearby, so we're going to see that show up almost right away. Right about now. There it is. Yeah, there we go. Hey, Fantasy, how are you? Fantasy says, when they measure these distances, do they account for gravitational dilation? I'm not sure what you mean by gravitational dilation, but I'll take a stab.
Time dilation?
I'm guessing what they're talking about here. Thanks, Sean.
You're going to be eating cat food, Farva.
Yeah. Sean's a good guy. And Sean, I want to know if you're still reading the book yet. Because you said you got our book, my book. I want you to let me know if you're starting to read it yet. If you have any questions.
I think he said he was on his second reading.
Oh, I didn't see that. I'm sorry. Okay. All right. So a little more here. So as far as what do they account for judging these distances? Okay. We judge distances by looking at the spectra of distant objects. And what happens is the spectral lines, when an object isn't moving, are in a certain place in the spectrum. And what are spectral lines? Well, I'll give you an example. The sun's core is much, much hotter than the outer envelope of the star. So that radiation coming out, some of it's being absorbed by some of the elements in the sun's envelope. And those show up as dark vertical lines in the sun's spectrum because of the way we actually get the star's spectrum, spread the light out. And those dark lines are called absorption lines. Makes sense because it's absorption by other elements in the sun's atmosphere. Well, because the sun is so close and not moving away from us at all, we see those lines in specific places. And those specific places, you assign a number, an actual frequency of where they're located. And they are in the range of nanometers, a billionth of a meter. Okay, angstroms. You could also make them extremely, extremely small centimeter ranges, but we talk about it mostly in nanometers. It used to be angstroms, now it's nanometers. So,
and they're at rest.
And that's what I mean. Yeah, that's when the sun is not moving away from us. They're just sitting. The lines aren't moving at all. But if we look at a star that's moving away from us, then the star's lines that we see in its spectrum are going to be shifted a little toward the red end of the spectrum. Now imagine you're an astronomer in the 1800s, 1700s even. No, let's say 1800s because that's about the time when spectra were actually coming into their own. And you took a spectrum of a star and you saw that the lines of hydrogen, okay, there's several series of hydrogen lines. One's called the Balmer series. Okay, hydrogen alpha is one of the Balmer lines. That's one of the lines that we talk about. And you saw that the lines were shifted in that star. You go, what the heck? Why are they shifted? They're shifted based on how fast the star is moving away from us. They could also be blue shifted based on how fast the star might be coming toward us. Okay? And so that shift in the lines can actually give us the distance to the star, the speed of the star that's moving. And when we look at distant galaxies, we have a whole different thing in play. We see the lines also shifted. We see all the light, every single line of all the stars grouped together that the galaxy is giving off are shifted toward the red end of the spectrum because it's going away from us, accelerating away from us at high speed. And that shift is what we've called, and you've heard Daryl say it too, the cosmological redshift. And that cosmological redshift is how we determine the distance to these galaxies. Because at certain distances, they're expected to be moving at a certain speed. And if we say that this redshift is a certain value, we know that this galaxy is a certain distance, moving at a certain speed. And that theory, okay, has held up under scrutiny. The only time it's actually provided a problem is when we've discovered that the universe was actually accelerating and isn't sort of just expanding at a constant rate. The expansion is actually going faster and faster every second, basically. And that's that's why we bring in the nemesis of Daryl Mason, the concept of dark energy. It's my nemesis too. I think it's sort of a fudge factor for something we don't understand yet.
It is.
That's what I think.
But this is one of the big things that the Webb Space Telescope has allowed us. When we see those galaxies that we never saw before,
Yeah.
it's because they were so redshifted, because they're moving so fast, so far away, that they were no longer visible to the Hubble telescope, for instance. That we're seeing them deep into the infrared now with the Webb telescope, and they can still detect spectra from them and figure out how far they're redshifted, and thus how far away they are and how fast they're moving.
Yeah. And let's see. Who asked the question? Oh, Cyclone has properly phrased the question with caps. We like that. What's the largest star that you know? Well, certainly there could be larger ones, but one of the largest stars that we used to know is the star UY Scuti and also VY Canis Majoris. That's the designations for these two stars. These are absolutely massive stars. However, those have now been eclipsed by another star with a very romantic name of R136A1. Okay, R136A1 weighs in at something like between 150 to 320 times the mass of the Sun. That is a massive, massive star. That star would certainly, if placed where the Sun goes, go well past the orbit of Jupiter, possibly Saturn. That's a massive star. All right, massive star. Maybe even more. So there's some pretty big hydrogen furnaces out there, let me tell you.
Let's get cooking on M33.
I know. What's going on here, Daryl? Why didn't you start the exposure? Oh, because I'm doing it. Oops. Yeah, I know. We'll do a 45-second on that, too. What do you think?
Sure.
Yeah, sorry, folks. I get wrapped up in talking. Okay. But I was giving information.
Well, yes, there are a lot of questions tonight.
Yeah. John G., that's right. R136A1. That's the biggest star now that we know. Oh, okay. Cyclone asked and you responded. Very good. Thank you, John. So more energy is emitted to someone as it moves towards someone. No, well, not necessarily more energy. The same amount of energy is being emitted, but it's higher frequency. It's shifted to the higher frequency. All right, but that's a very good thing that you added, and so you have won moderator status, John. I've made you a moderator. Good question. Good questions get you wrenches.
Ta-da.
You got it. Yes, I'm good. See, now you've seen it, that's fantastic. You look it up. Okay, so we have another exposure coming in here. Let me just make sure we're going well here. I'm going to zoom way in. And when you see the second one come in, you see all this noise in here? A lot of it's going to disappear. I've talked about this before because the stack process takes it away. Watch. Boom, look at that. A lot of those colored modeling things went away. And right now it looks kind of rough, but as we take more images, it's going to look gorgeous. So let's add the mask, sharpen it up a bit. We're doing 45-second exposures here. S1218 is now considered to be the largest star in the known universe. Well, it's a moving target there, Cosmic Ray. As I mentioned, you're right. Today's R is tomorrow's S. Hello, Taryn.
I tend to discount things like that. You see them in videos on YouTube. Biggest this or that in the universe, and well, the universe is a damn big place, and who knows what's out there farther than we can see.
Yep. Hi, Jim Merrill. Welcome, Jim Merrill. Nice to have you here with us at SkyTour LiveStream. We are imaging Measure 33. This is live. Genghis, I didn't say hi to you before. I am so sorry. Nice to see you as well.
Can I ask a question?
Of course. Well, can I ask? Let me just say one thing. Cindy, I noticed you hid Cyclone. Was there a reason for that? Cyclone, I know him, and I don't have anything against Cyclone at all. So I hope that's. I don't know what you saw, but let me know, because if Cyclone did something bad, I'll kick his butt too.
He typed the alphabet.
Oh. Okay. All right, no problem. You'll be back in a minute, Cyclone. Not to worry. But thank you, Cindy. Your diligence is remarkable. Thank you very much for helping out. Yeah, Daryl, I'm sorry. What's your question?
The red response of your camera.
Yeah.
I see images of M33, and there are red patches all over it. And we don't seem to see that so much with this camera. Why is that?
Well, I think you pointed it out. I mean, it could be that the red response is not as good, or we're using a filter that lets in some of the red light, but it's not a narrow band set of images. So we're not getting specific H alpha or the red responses for the rest of you who know that. So it could be that those were narrowband images, maybe. And this is the UHCS, which is a combination of the H alpha. Then you have the silicon 2 or sulfur 2, and the O3, oxygen 3. So depending on the bandpass, maybe that. I don't know.
I read something about even narrowband filters working at f2, like on the Hyperstar or the Fast Star systems, that can throw off the bandpass, I guess.
Okay.
Could that be a factor?
Maybe. I don't know. Okay, we stacked 7 here. Let me just check out the stars. I'm wondering if I need to refocus here. Yeah, I do. Okay. All right, I'm going to pull us out of this and get rid of the stack. Don't worry. And I'm going to go to our night vision mode, and then I'm going to do a focus again, because I forgot again to turn on temperature compensation. My bad, folkses. Alright, so we're going to do multi-star, full width, half maximum. Yes, that could be it, Daryl. I'm not... I don't even... I don't have an understanding yet of what the bandpass is for the red end of this thing. I mean, I saw it's fairly narrow. I mean, like it should be, right?
You'd think. Well, that's something I've seen around a couple of times.
Yeah.
On YouTube, they were talking how ultra-fast F ratios can affect the narrowness of the bandpass or something of the sort. A little over my head, I guess. I know some people that they still use DSLRs. There's always a big argument between the Nikons and the Canons. Some say the Canon DSLRs have better red response than the Nikons do.
Yeah, it depends on the sensor. Like for the Sony A7S II, right? It's the Exmor sensor, and that has a certain red response. It may not be the best, but you get a certain amount of it, you know.
And I believe on both of those cameras, there are special versions or setups people do or get different sensors or something to improve that red response.
Yeah, I wonder if they just do add-on filters.
And that may be the case too.
Interesting. Okay. Well, we're going to be focused. We found our best focus. There you see the line. Again, we're building this parabola here, which gives us a focus range, out of focus, in focus perfectly, then back out of focus. And then we get a green line like we got up here. Now we can say, go to that best focus. And away it goes. And then it goes all the way back out of focus and then comes right back in to the best focus. And there it is. And now we're perfect. Okay. And what we're going to do now is redo this exposure again for 45 seconds. Now we're going to go in. You're going to see the previous one, okay, in the live stack here. All right. So you can get an idea why I redid this. I'll show you. Zooming in. All right. Do you see how the fainter stars look out of focus a little bit? That's not good. That's not good. So we're going to clear that, and we're going to have a much more tight, focused shot. Yeah, okay. That was kind of funny, Ray. Ray says, M33 makeup artist ran out of rouge for tonight's broadcast. Well, that's true. I guess that's true. Okay, see, now there's a difference, right? Look at that. Wow. That's a pretty good. Well, it's pretty good there, Marc. What can I tell you? Oh, yes. Yeah, and you can see this beautiful hydrogen alpha region. As Daryl has told you guys, it's NGC 604. It's a hydrogen alpha region with these beautiful tendrils around it. This is one of those objects that would benefit from smaller pixels. Now, when I say pixels, if you look at your zoom right in, okay, you can see each of these tiny squares is a single pixel. All right, and then the next camera that I want to get for this telescope will have extremely small pixels, so we'll be able to zoom in more with even if we had a hyperstar on it, and be able to see some tremendous detail. But we'd have to get matching cameras. I'd have to have
what?
Matching cameras. I'd have to have the same camera on this telescope as the new telescope.
Oh.
Yeah, just to keep everything equal. Marianne was down in another town in southeastern of Tucson, because we're west of Phoenix, and then you go 2 and a half hours south to Tucson, and go another hour southwest or southeast, and you get to this small town that we're looking at for the next potential observatory, and it's actually a beautiful little town. And we've got people that are interested in us, putting an observatory on their land, and we could basically rent it from them, basically. Okay, so look at this little guy right here. Isn't that something? Look at that. You got a beautiful roundish nebula there right next to what could be a supernova remnant. Another supernova remnant. And then down below here is another supernova remnant. Way out here.
Some of those look awfully big for supernova remnants. When you compare them against the size of the galaxy as a whole, they're pretty darn big.
Yeah, but that's what I would expect. They just expand outward. Look at the size of NGC 604.
Yeah.
Let me see. Do we have the enhancement off right now? No, I'm gonna turn it off because I wanna show the core of this galaxy.
Well, yeah, and for what was said earlier, when we were talking about the so-called metallicity of stars, those green areas, that's the characteristic color of O3, oxygen 3.
At the very least, yeah.
And that came from great big stars going boom.
That's right. And it could also have been in those stars' atmospheres and liberated as well. And undoubtedly, that's true. And you know, both of those things are true. What Daryl said is true. What I said is true. There's no reason why not. In fact, remember I told you oxygen is the third most abundant element in the universe. Hydrogen's most, helium next. Oxygen is third most abundant. So it stands to reason that a nebula from a supernova is going to show oxygen in it, and hydrogen. And then other elements less so, because there's going to be a predominance of hydrogen and helium and oxygen. Helium has like a blue line, which is really interesting. I have some gas tubes here that I do gas tube experimentation with, and you can actually see, and when you put high voltage through these, you actually can see these amazing color spectrum of these emission lines from these different elements.
When we see green auroras, northern lights, or southern lights as the case may be, I understand the green comes from oxygen. And Izabela and I had a talk the other day about the green tails of the Leonid meteors we saw also comes from oxygen, but that's not the same as oxygen 3, is it, or is it?
I don't think it's doubly ionized oxygen in that case, because doubly ionized oxygen is extremely rare. It doesn't occur on Earth. It only can occur in the rarefied environment of a nebula. So I'm not sure what that color transition is. But oxygen will generate more than one transition color, and the green could also be due to a different transition. It's also possible that it's nitrogen as well, interaction with nitrogen as well. It can also be that a meteor that has any kind of additional metallic content can burn green when it's ablating, but the tails are green and they make like these auroras, and that's a disturbance in the ionosphere. So the tail is actually an aurora that is based on the atmospheric composition of the Earth. Yes.
Right. We were talking about that, and I looked it up. And, she was wondering because the head of the meteor was white, and it was moving, and the tail was being left behind and just sitting there in space or in the sky, and it was green. She was wondering why. I looked it up somewhere, and they said it was oxygen.
Yeah.
Just ionized oxygen from the atmosphere.
Yeah.
And then it would fade away.
Yep.
As it cooled off and lost its ionization.
Yeah. The electrons came back into the atom, and they give off that typical color. I mean, it actually, when you look at it up in that high in the atmosphere, 90 miles up, it's still a denser location. That's a much denser, very, very high density location compared to a nebula on a supernova remnant. So we're still talking many millions and billions of atoms per cubic centimeter. Millions, well, probably several hundred million, right? I'd have to look up and see what the density of air is at 90 miles. But in a nebula, you're looking at a handful of atoms per cubic centimeter.
Yeah.
And it requires that in order to do the oxygen 3 transition, but that's why it's called a forbidden line. Look at this. This is really pretty, man.
Izabela had an interesting question. What is the most abundant molecule in the universe? A molecule from 2 or more different elements, she means.
Okay, well, the most abundant molecule in the universe is probably going to be diatomic hydrogen.
Well, she said from 2 or more different elements.
Well, okay.
And we immediately said water, maybe.
I'm sure that's up there. I'm thinking carbon monoxide, CO. Now think about the energy required to make a molecule. What molecules might be easily made? I know that there's carbon-carbon molecules. That's what the dark nebulae are made of. A lot of cases, conglomerations of silicon atoms to make silicate dark dust based on silicon and dark dust based on carbon. So it might be that the dark dust in the universe, which is multiple silicon atoms with ices on top. Tough question. I mean, because you don't have it's like having, if you want to talk about a unique molecule, well, carbon monoxide is unique. Cyanogen, CN, is unique. And cyanogen, remember, also glows green, like oxygen 3. So,
well, offhand, I mean, you said yourself, if hydrogen is the most abundant and oxygen is third, that maybe hydroxyls at least, if not water.
Yeah, but it takes energy to make them, and in the dark clouds in the universe, that's where they're made. So it's possible, but I'm thinking universe. I'm thinking in between the galaxies. I'm thinking, within the galaxies. But I guess or dark nebula versus bright nebula. You're not going to have water in a bright nebula. But you will have water in the dark nebula in the form of ice, for sure.
Mm-hmm.
Okay. Or methane, yeah, that's right. You have methane. Martian Johansson trying to offer that up. That's true. That's a hydrocarbon. It's a complex molecule. It's very simple. It's based on the fourth most abundant and first most abundant. So that'd be a lot of that. Methane would be quite prevalent out there. And Cyclone 2 is asking, what's the strangest thing you've seen in space? Well, someone talking about thongs in space. That's per your question. Wow. I'll have to think about that. Strangest thing we've seen? Well, okay, I do know the strangest thing. Daryl, you were here with us for that. Maybe we actually caught something moving in a very tight circular pattern over the observatory on the all-sky camera. Do you remember that?
Yeah, I remember you talking about it.
Yeah.
Showing me an image of it.
Yeah, let's do an acquisition here.
It wasn't really in space, though, was it?
That's true. Let's see. Let's just check this out. Let's look at our sky. It'll be dark now. Oh, look, we've got clouds. But those are heading to the east. So they're leaving us behind. And we're actually... we're up... where are we up? We're up like... we're up here somewhere. So we should be covered. Alright. I had to reverse everything in my head. You know what? I just to your credit, Daryl, when I went out there, I tried to see what was involved in getting that camera and spinning it the other way. Then I thought, there's got to be a way to do this internally. Just rotate the image. There's got to be a way. So I figured there's a way to do that. And rather than monkey with hardware, I figured I should be able to do it software-wise. And I haven't done it yet, to my discredit.
I would think there'd be some easy digital way to do it. Just
I agree.
Flip it top to bottom.
Without making it go backwards, yeah.
Yeah. Cyclone, there are meteors every night. Will you see them? Who knows?
Yeah, the meteor storms, meteor showers occur at certain times of the year, but the Earth attracts thousands of tons a night of material. Actually, more than that. I'm trying to remember. the amount of tonnage per night of meteors. It's actually a very, very high number. Thank you, Sean. Yeah. How much meteoric dust hits the Earth is a function of, I guess, what dust is in the atmosphere, you know? I'm sorry, what dust hitting the atmosphere on the dark side when it gets nighttime. But it happens during the day, too. Can't forget that.
You know, I've wondered in the past, and I've heard it said that this is not so, but that yes, I mean, Earth is collecting thousands of tons of meteor dust a day, and yet has that contributed significantly to the mass of the Earth over the 4.5 billion years of its existence? And they say no. You'd think that would add up over time.
Well, it depends how the dust gets processed and what happens to it, right? You know, so basically, it's about 5,000 metric tons a year hits the Earth, right? So if 5,000 metric tons hits the Earth every year, that doesn't really add up to a whole lot. I actually thought it was more significant than that, to be honest. And Marcin Johansson says, hey, you guys remember the finding of the source of zodiacal light in the night sky? Yes. Remember that time I saw the zodiacal light and I thought somebody had their lights on. I was getting all pissed off at the observatory site. And I'd never seen the zodiacal light. And that's what I was seeing. Yeah.
Yeah, Marcin, some people have been saying recently they think it's coming from the planet Mars. They used to think it was just general junk floating out in the ecliptic plane. Well, nowadays they say it's dust from Mars.
Well, undoubtedly that's part of it too, though. I mean, the holdover from the formation of the solar system is still there for sure. But we also have major impacts that hit Mars, spewing lots of dust into the solar system, which eventually would form a ring around, the solar system, and that would be a ring of dust, and then we would have zodiacal light 2 times a year.
Yeah.
Yeah. So.
I said before, when March of 1997, when I went up in the high country on the top of a mountain pass and took pictures of Comet Hale-Bopp. I was stunned by how clear the zodiacal light was that night after sunset. Just a huge kind of a tilting triangle of light over in the west, leaning toward the south a little bit. And it was the color of sunlight, and it was obvious instantly what it was.
I had never seen it before, so I didn't know what to expect. So it wasn't obvious instantly to me. All right. This is coming out very nice. This is it shows you the spiral structure here very clearly. You follow these dark lanes, and they tend to outline the spiral arms because there's the spiral arms that have this dust in it, and then of course the stars themselves, where they form new stars. Look at this. There's clearly a spiral arm there. There's a spiral arm here. Okay, and look at this one. It's like it's fractured, and little pieces coming off it, little tiny hot spots that have become separated. You see that, Daryl? That's interesting. And we got one here. We got one here. Tight ones here. This is interesting because you wouldn't expect that there would be non-uniform arms. But this galaxy, even if it's at an angle to us, okay, I mean, it's clearly not face on, 100% face on. It's at an angle, a slight angle, and maybe that angle is like this if we're looking in the image, okay? It's like upright. Even so, the spiral arms are shaped really oddly. So this, I think, is why some people thought that this galaxy has interacted with the almighty Andromeda Galaxy.
Right.
And it's possible that that's happened. Alright, let's see here. We've got 24 stacked. We'll go to 25, staying consistent. And let's see on our enhancements. Okay, we got the unsharp mask on. We turn it off. We'll look at the core, measure 33. Look at that, right to the core. That's beautiful. Why, I can see the supermassive black hole. Very nice. Okay, now we'll pause it there. And we'll specify measure 33. Galaxy. Alright. Alright, there we go. And this is again 2.7 million light years away. Absolutely beautiful. And just to say it, there's the nameplate. Measure 33, Spiral Galaxy. Okay, we'll show it in its entirety now, just so you can have some fun with it.
Izabela, I watched a little bit of the Orion moon approach, lunar approach. The moon looked really distorted in some of those images. It was almost like a teardrop or a fisheye effect or something.
I think the camera obviously did in fact do that. Pretty clear. Hello, Judy. Judy McClelland is here. Hi, Judy. Uberku, how you doing? I don't think I said hi to you yet. I apologize. Okay, this is just gorgeous. This is just gorgeous. Wow. Let's try and let's do a close up here. Smile. Smile, measure 33. Look at that. Wow. Let's see if this guy right here changes by taking off the unsharp mask. Do we see a little... Yeah, see a little more detail in it now. Look at that.
Yeah.
That's nice. All the way to the core here. Look at these bright, tight star loops around the center of the galaxy right there. That's gorgeous.
Somebody, might have been Izabela, I forget, said that M33 does not have a supermassive black hole in its center. I don't know.
Possible. I'm not sure. I'm not sure about the research on Measure 33. I mean, we can actually, if I increase this, let's go crazy. Watch this. We're up to 4. Look at how the unsharp masking can make it look like way too much. And then down to 1.24, a little too much. And I've been using like right around 0.91, maybe let's go a little less, 0.87. Hey guys, give me a thumbs up out there, will you? Give us a thumbs up. That helps us a lot. Looking to make our mark on YouTube to help you guys. We still want to, we're actually paying Starlink to do our internet. So that's costing us $110 a month on top of the $600 it costs us for the service. On top of the $20,000 we spent on building and telescopes so far. Actually, 18. So that's a lot of money. But I just love bringing this to you. Wow, look at that. Wow. Okay. All right. So that said, let's come in here, and we'll do it again. We'll save it now. Save exactly as seen. And then we can clear this beautiful galaxy. And that'll be up on the data page in just a few seconds. Doesn't take long. That's one thing about Starlink. We get our objects pumped up to the cloud very, very quickly. So as soon as we take a picture, the image you see here on the screen ends up getting shot out of the observatory up to the cloud, where it ends up being stored on a server that's free for you to use and go into. Per Cosmic Ray's advice the other day, I've added a blog to SkyTourLive.com, which will announce our streams, and that's getting sent to Facebook, Twitter, and it's on SkyTourLive.com. So you'll get an announcement, even if the YouTube, even if YouTube isn't working right. So I can't stand that happens, but that's what happens. We don't have it's not good, but it is what it is, right? So I want to welcome the 45 of you that are watching right now, and I encourage you to talk and chat. Let us know you're there. We'll say hi. If you have any questions, let us know. Louis Taz here. How you doing, Louis? David Schmidt is here. Hey, David. Wow. Okay. Next item here. Let's bring back the telescope. All right. There we are. And let's get our computer back. There it is. Right there. Okay.
I was thinking the other night, looking at this and some of the others galaxies we've seen this time of year lately, that though we always talk about springtime as galaxy season.
Yeah.
That of the 1,000 brightest galaxies in the sky, 3/4 of them are over in the springtime sky, from Ursa Major down to Virgo.
Yeah.
Some of the best examples are this time of year. M31, M33, 253.
Yeah. Oh, yeah. Yep. Let's see. Yeah, I don't want to do that now. Oh, you know what? I know something we haven't looked at a lot. And we certainly haven't done a longer exposure of it. I'm not going to do Heart and Soul. We did that already. But I'm going to come up here. Get us into Cepheus. So I'm thinking... I did this as a private thing the other night, and I'm wondering if this is it.
What is it? Is it a secret?
Oh, it's 7822.
Oh, okay. I see it now.
NGC 7822, guys. This is really interesting. This object showcases a huge number of different phenomena that the universe has to offer. And you'll see them pretty quickly here. As we're zooming through the space in the universe at high speed here. And then we come up to this reddish thing that's in the view here. What is that? Well, we'll find out. We will find out. You will see. All right.
Usually in Stellarium, when you see a big area that they have all lit up and stuff in it, there's something good inside there.
Yeah, I know, right? Especially if there's lots of stuff that's just hanging out. I can't wait to start imaging the Spaghetti Nebula, which I don't think we're going to get to tonight, but let's go look at the all sky camera again. Make sure that our north is up here right now. So let's go see. We're right around here. We're actually right about there. So let's make sure that we're okay here. This is from a little while ago, so this should be over more this way now. Yeah. Okay, we are clear. Mission is a go. All right. Okay, this is NGC, otherwise known as New General Catalog, 7822. It's a hydrogen emission region, otherwise known as a stellar nursery. Cyclone retracted his message. Why did he do that? Okay, so let's do, and we're streaming. We're doing our. We are. I want to just get 45 seconds out of this here. There we go. Okay, 45 seconds out of night vision mode into live stack mode. Here we are. And let's bring this up for a sec. And stop the auto hide for now. Dock it. There we go. Yeah, Cyclone, we take suggestions. Thank you, Cosmic Ray, for that information. That is a good deal of information. Thank you. All right. Again, the first one is going to be a little rough because of the noise, but once we stack again, just to make an image sandwich, aligned and stacked. So we end up getting some really pretty images. Ah, look at that. That's beautiful.
I like that processed image you did of this.
It was that pretty. All right. There's a lot of. The other night I did a private stream to see what it looks like because we haven't looked at it in a while, and I wanted to see how it looks. We have a satellite here. Interesting. The next exposure of the satellite's going to be, there it is right there. And then there'll be another one. This actually is a satellite that's actually doing this. It's a tumbling rocket body doing this. So when it's like edge on like this, it's very bright. When it goes like this, it's less bright, and then it's more bright. If you notice, the next one is going to be a faint line followed by a bright line again, which we'll see here.
Ronald says hi, Mark.
Is he here? Hey, Ronald. How you doing, Ronald? All right, here we go. Watch this. Right here, we're going to see the next line of the satellite. There it is. All right. So that'll, again, disappear over time.
Looks like it's tumbling.
It is, yep. Yeah, I just mentioned. Did you see what I did? Oh, you didn't see what I was doing, but you heard me say it. I showed them with a chapstick. I was tumbling it and showing them how it actually tumbles. It's a tumbler for sure. Now, I have it set up in my processing program, which is just Photoshop. It knows the scale of the photograph so that when I measure something like this, we can actually measure the actual height in light years of objects like this and calculate just how big they are. And that only works for objects that are like right flat to us. If it's sort of on an angle, we're going to get a false reading, right? Because we'll measure from here to here, but we're not going to measure from here to here. Okay, we're going to just measure, from here to here. So that's going to be a smaller value than what the actual height is because it's projected into toward us or whatever. That's it. Ronald from ERRT Radio is with us. It's about time, Ronald. Where the heck you been, man? I'm waiting for you. For days. Haven't heard from you. Now quit your laughing. Okay, so now that we're in about 5 stacked images, you can see that we're seeing some more definition in here. Really nice. Let's see what they want to do with it. Okay, that's pretty cool. Look at that. That's nice. I just wanted to mention to you guys, we may see each other one more time before Thanksgiving, but if we don't, I just want to wish you a happy Thanksgiving.
Does that mean tomorrow night?
Oh, it's just, what's today?
Tuesday.
Yeah, so yeah, if I don't see you, if we don't stream tomorrow night, yeah. But you know what? There's no reason we wouldn't stream on Thanksgiving night, except for the fact that no one will be here. Well, I'll be here, but the people watching may not be here because it'll be a holiday.
I'm going to be rather busy Thanksgiving night.
Yeah, so it's probably not a good idea.
I'm going to be rather busy tomorrow night, too.
Okay.
Might be able to take breaks away from it, though.
That's all right. You be cooking?
Yeah, prep and cooking and stuff for Thanksgiving. And Thanksgiving night, I've got some post-processing of my own to do.
That's cool.
Making the fixings for turkey soup.
Very good. Yeah, I'm not sure we're doing anything this year because right now in the house, there's COVID running around in the house here, so we're kind of isolated. I don't have it, you know.
You should call in a pizza. Can you cook turkey? Can you make a turkey dinner?
Never have.
I make a heck of a turkey dinner. I've gotten pretty good at it. But one of the more memorable Thanksgiving dinners I ever had was we went out for pizza one night. It was surprising
cool.
how many people did it.
Oh, I believe it. I believe it.
Place was full. I guess they got their fill of turkey at lunchtime or at dinner time.
Yeah. Wow. Well, this is NGC 7822, guys. I just wanted to share with you. If you notice, here is the young cluster born in this nebula. That's the reason the nebula is glowing. Very likely because these stars are hot and young, and their ultraviolet energy is ionizing hydrogen all throughout this cloud. This black dust, on the other hand, is up here in front of this nebula, which is back here. If you see me down the lower left, there's the black nebula. Here's the actual nebula. It's behind it. So it's continuing to glow behind all this. Okay? So those aren't voids. Those are actually clouds in front of the bright nebula. And if you look, you'll notice that there's these pillars of material that are reaching right out toward the cluster. Same thing down here. Pillars reaching out toward the cluster. Why is that?
I always like those two there.
Yeah.
Got the big one and the little skinny one next to it.
Yeah. Well, the reason this is happening, we got one here too. The reason this is happening is because these stars have a lot of hot ultraviolet radiation and very, very powerful stellar winds. The combined stellar winds from all of these stars in this new cluster are blowing out. And what they're doing is they're opening a cavity. You can see part of the cavity here. The stuff is thickest over here, thinner in here, okay, and thinner here, and then it gets, convoluted by more dark nebula out here, so you can't really tell what's happening here. But it's hollowing out this entire region of all the majority of the gas and dust that it was previously ionizing. So most of the gas being ionized is now on the fringes instead of in the center. But this stuff where it's actually denser, where there's dust concentrations in here and here and here, there, okay, that stuff actually doesn't get evaporated by this hot ultraviolet radiation and the stellar winds from these stars. It's resistant to it, and it acts like a shield and prevents the stuff behind it from being eroded away. And that's why these pillars exist. All it takes is having one area of density, and then the area behind it, if we zoom into this, you see it very clearly. Okay, all right. The area behind this dense nodule at the top is protected. The area behind this is protected. All right, and that's why this material is still there. It's not being evaporated as easily because the starlight can't, its stellar wind can't hit this directly yet. Maybe at some point this will, if this erodes.
And the process is exactly the same as when we see the pillars of creation in the Eagle Nebula.
That's correct. Messier 16 is the same thing. We've got those fingers sticking up the same way. Those are stalks that are being evaporated by hot young stars in the cluster. And maybe they'll be fully evaporated someday, or maybe the reason that they're not evaporating is because they're dense enough, because it's a self-contracting, gravitational contracting cloud that will eventually become a star or a star system with planets around it. But the prevalence of very hot and powerful stellar wind might make it difficult for planets, but we don't know. It's possible. But this is a really beautiful region right here. I like this. That's really pretty. Let's
Mark,
get a close up.
Excuse me a moment, please.
Sure.
Be right back.
All right. So look at this now. So we're gonna just check this out. Let me get rid of this guy. All right, let's zoom in on that. We've stacked 14 of these. Isn't that something? Look at this beautiful. Look at how complex this is, guys. Very, very complex. Again, this is NGC, or New General Catalog 7822, Object 7822. Yes, I know. Such exciting names, huh? Well, some of them have names. Some of them have names. But this is a stellar nursery, and it's just really pretty. So this is what it is right there. All right. And the part we're looking at right now is here. You see this dark dust? Again, that's in front of the nebula, and the nebula is behind it. You see a similar thing, actually, very much so, with the North American Nebula. Wow, that's really pretty. Yeah. So if you can just see past this, you can see that here is the rest of the nebula right here. It's behind this veil of dark dust, which is partially shielding it. And this is a carved out cavity made by these stars. Here's the carved out cavity. It goes all the way up around the top. So that's what these clusters do. The most famous one that you probably know is the Rosette Nebula. If you look at the Rosette Nebula, it's got an open central cavity with a ring of these H2 regions around it, right? These beautiful glowing hydrogen regions. And that's, again, because those hot young stars are clearing the cavity around the cluster, clearing the gas and the dust from the middle with their stellar winds. And Robin Curtis is here. Hey, Robin, otherwise known as Database Girl. How are you? Robin is single-handedly responsible, with only very little of my help, in cataloging every observation that SkyTour LiveStream has made over the last year and a quarter, in a database. And we're building a front end so you can all search and find out every version of this that we've ever done, for instance. Look at that, Daryl. Look at that.
Oh, yeah.
That's really pretty. I want to see if we can draw out some more detail here. Well, actually, let's go here. Let's see how much more we have. Okay, that's a lot. Too much. How about if we back out of that and come down here?
This is like the Eagle Nebula on steroids.
Right? Yeah, we can see it better anyway. Alright, so there. Let's cut in the contrast a little bit. Look at this one. This one is like a point. Look at that. That's like a little point. I'm not sure if this star is in there and responsible for any of this, or if that is just a foreground star. It may just be a foreground star.
Cyclone, it's a region of star formation. It's a big dust cloud. It has it's a stellar nursery. Stars are coming to life in there, like in that cluster up toward the top. There's a lot of material there, and the cluster and the bright stars are illuminating the dust and the gas and making it shine. And this is what we get.
Yep. I kept that cluster just in there so you could watch for yourselves and see how this stalks here are in line with that cluster of stars. It's very common to see these stalks like this. And we call them pillars or stalks.
Or elephant trunks.
Or elephant trunks, yeah, that's right. Yeah. Which is our next logical stop. Okay, we've got 20 stacked. That's good.
I knew it would be.
Oh, I bet you did.
Well, this is in Cepheus, is it not?
Well, I will check. I'm not quite sure.
I see almost like a skull face, like Skeletor. You see the two bright stars or the eyes?
Oh, right here?
Yes, and then his nose is below that, and his jaw and teeth are below that. There's his teeth.
Yeah, I see it.
Lower jaw.
I get you, He-Man.
Looks almost like he has horns.
Oh, yeah, right here and here. Yeah. You know, we've imaged 7822 in the past. We've never seen all this nebula out here. Let's push this just a little bit, capture a little more data. And now, if you'll notice, you can see it's more obvious that this dark stuff is sitting on top of the nebula. See that?
Those aren't horns, they're ears. It's like he has pointed.
Yeah. Right here, like an ear here, like a little tiny dog ears either side. That's cool. Hey, Dan Norton. Nice to see you. Thanks for coming. Okay, this is for you, Cyclone.
We are looking at the nebula, young Skywalker, the place from which young Jedis are born.
Is that better? That was the Vader bottle. That was my my Vader bottle. It's a bottle that perfectly mimics Darth Vader. I've had it for over 30 years. Won't break it. If I break it, I think I'll just cease to exist. My Vader bottle! Oh! Cyclone had asked if I could speak about the nebula in a deep voice. Okay, so let's we're 23 here. That's good. About to go to 24. Let's see if we can pump up some more detail here. It's a little much, but let's see if we can drag the black level back a bit. Kind of get more contrast out of it.
Well, the face really
Oh.
popped. You lowered that.
Look at that.
Yeah.
That's beautiful. See, you can see it's embedded in this nebulosity all out here. You know, all this out here. Wow.
Oh, gee, I was thinking that Darth Maul Nebula.
Darth Maul Nebula, that's it. Hey. Oh, Daisy and the Cowboy. Hey, it's Mike and Daisy. How are you guys? Good to see you. And hi, OG. This looks nice.
It does.
See, these are the colors you expect to see in the universe, right, guys? It's really pretty. Right now, get my telescope back now.
Just wait till we get to see the Boogeyman Nebula, folks.
Oh, yeah. Boogeyman is just stunning.
Yeah. He's a little east of Orion, so we'll have to wait a while for him.
That's all right. We'll get there.
That's trippy looking. I'd never noticed it like that before.
Yeah. Well, we added some more processing like we haven't done before. Let's pull the name out. We don't need that there. Okay. Now you're looking at it. Look at that. If you see where the telescope's pointing, it's pointing out the back of the building. That's toward the north. So this is up in the north. And you asked if it was Cepheus before, and I think that it's on the border.
Yep, right there.
Yeah. And
That's right. Actually, that's the border of the constellation right there. Yeah. So,
yeah, so we have Cassiopeia and we have Cepheus.
yeah. It's right between the two.
It's right between the two, yep.
Yeah, the king and the queen.
Yep. And there's one called the Little Rosette. Have you ever seen that one?
Yeah, we looked at it last stream.
No, we didn't.
Oh, that was
Yeah, we're gonna look at the Little Rosette next. Gonna show you that.
that was the Northern Lagoon.
That's right, Northern Trifid.
Or Northern Trifid, yeah.
Yeah.
I think
Okay.
we've done the Rosette before, the Little Rosette.
I think we have.
Where's a look?
Yeah. Okay. Well, we've got 27 here. We're gonna pause it, and I'm gonna change this name up here to NGC 7822, and it's an EN or Mission Nebula. And
Boy, that.
what?
Oh, that's about a goblin-looking face there.
Isn't it though?
It's interesting.
Kind of reminds me of Predator too.
Hmm.
Yeah, and save exactly as seen. So this is being shipped out, and this image, exactly as you see it, is going to go to the cloud and be available for you to download and have fun with. The only thing you can't do is sell these images. These images belong to SkyTour LiveStream, but you are free to use them, put them on your background, do whatever you want. Except sell them. Okay. Alright. So now we come in here and we'll clear this and get rid of the stack. We don't need it. Go back to 1 second and maximize. Wow, look at that. Okay. Here we are. Okay. Okay, so now we are in our night vision mode, and we're going to go up just a little bit to the next object we want to see, which is the Little Rosette Nebula. It is kind of a little rosette. It sort of looks like a little rosette. It doesn't. We don't have to go far. It's just south of this thing. Here we go. All right. So you can see it here. You can start to see it here.
Daisy and the Cowboy says, I see Groot.
I see Groot.
I have always wondered, I mean, you know,
I am Groot.
what's his face?
It does look like Groot.
What's his face was the voice of Groot.
Who's that?
Riddick.
Oh. With Chronicles of Riddick.
Yeah.
What's
his name?
Yeah, Fast and Furious guy. Not Fast and Furious. What's his name?
Yeah, oh, it was Fast and Furious.
Okay. Yeah. I can't remember his name. Someone in chat will.
Jesus.
No, not Van Damme.
The bald guy.
Yeah, the bald guy.
Yeah, Vin Diesel. Thank you.
Vin Diesel. There you go.
Yeah. I mean,
Thanks, Sean.
He was the voice of Groot. But
I am Groot.
all he said was, I am Groot.
I am Groot. That's all he said.
How much did they pay him for that?
I don't know.
All he had to do was come in and do 5 minutes of work and say, I am Groot. And, you know, then he got to leave. He said, we are Groot as well at one point. But,
yeah.
The first one.
Yeah, so they got him for like a half a day to just say, I am Groot. 14 different ways. I wonder if he had any complaints. I don't know. I feel like he should say more. No, Vin. He just says, I am Groot. That's the whole point.
Oh, I'm sure he laughed all the way to the back.
He did, I'm sure. These
I want
guys.
to see him in something good. The movie that
the-
first made him famous, Pitch Black.
Yeah, Pitch Black. Yeah, Pitch Black was a good movie.
That was actually the first Riddick movie.
Yeah, if you haven't heard that movie, guys, it's a movie about this guy, Riddick. Okay, and the idea is that they're on a planet. It's a science fiction movie. They're on a planet where there's no moons, no stars, nothing. So there's no light whatsoever. And at night, it's absolutely pitch black. And of course, there's things that want to eat you when the lights go out. So that's what the movie's about.
Yeah. The planet orbits a multiple star system.
Yeah.
And it's never dark there. And then there's, I think they're actually on a moon of a bigger planet, maybe like a Saturn, a ring planet. And they see an orrery in the settlement they were checking out. And somebody's playing with it, and they accidentally cause an eclipse. And the planet goes in front of the stars, and all of a sudden it turns dark. And then all these nasty creatures come out and try to eat everybody.
Oh, was that the basis of it?
Yeah.
Yeah, because I did not remember what the actual basis was.
Yeah.
Okay.
And he was one of the passengers on the spaceship that crashed on the planet.
Wasn't he a prisoner?
He was. He was an inmate being transported.
That's what it was. These were inmates being transferred. That's right. I remember that. Okay, this is the little Rosette Nebula, which is interesting in its own way, but we'll check it out. It's going to be about this big, right about here. Here we go. And give it up for the little Rosette. Yeah, look at that. Let's check it out. Make sure that we are all good here. Yeah, we are. So this is the first exposure. You can see that it hardly looks like anything. And you say, ew, what's that? Well, with the second exposure, you'll see all that colored modeling go away as the first stack image is put on there to randomize the noise and to bring out the detail that's hidden by that random noise. And you'll see that here in a second. Actually, 4 seconds. 2, 1, 0, go. Boom. Okay, there we go. And so it begins. We'll see how this turns out. Ooh.
I see dark lanes in that picture.
Yep. There are some, I think.
Big one up at the upper left. There's one to the lower left, one or upper right, one to the lower right, and to the lower left there's a couple.
Yeah. What's interesting is what you're seeing here is an object that could have been the Rosette Nebula if it had been closer. So it's not closer, so we don't see. Let me turn this off for now. Turn off the unsharp masking so that we can tone down the stars a little bit. Izabela says she hasn't seen the little Rosette. Yeah. Okay. We're gonna let this develop and see what we get. Let's go back to our histogram, our data, and let's do what it wants to do. And we're gonna pull this down a little bit. Okay. There's some dark lanes in there for sure. Let's see if we can color correct it to make it a little more, that's the right color. Now if you ask about binary stars, you'll notice looks like everywhere you look you see pairs of stars, right? And like these two. These look like alberio, like an orange star and a blue star. It looks like sort of like an alberio type pair. But they're probably just line of sight. This star could be much closer or farther away from us versus this one. And some could actually be true binaries.
Did you know they're making a third Guardians of the Galaxy?
Well, yeah. I mean, they gotta get their money's worth out of Vin Diesel.
Yeah. What's interesting, they're going to be facing a guy called Warlock. Adam Warlock, who was Warlock had his own Marvel Comics back in the day, like back in the late 70s, I think.
Really?
And they're bringing Warlock back to be the foe of the Guardians of the Galaxy. Warlock was a pretty cool comic.
Rather than Chinny Chin Chin there?
Chinny Chin Chin?
Yeah, the big chin guy. Who was Big Chin in that? Who were they fighting against? The Big Chin.
You lost me.
Didn't they have? Was that the wrong movie? Maybe it was. Maybe I'm thinking of the wrong movie.
Oh, Thanos.
Thanos, that's the guy. Yeah.
No, those were the Avengers.
Oh,
Guardians
Avengers, Shemengers. Who knows?
Everybody was in those.
Yeah. Okay.
The two Thanos movies.
Okay.
Big chin guy. I had to think about that for a second.
Yeah. Okay. We'll let this develop a little more and then we will head over to our other location. First, align my system up here. Okay, good. Yeah, Thanos, that's the guy.
Yeah. Thanos actually goes way back in the Marvel universe, too.
Really?
Back in the 60s, I think.
I had no idea. I never followed the Marvel Universe in the past until the movies started coming out. I thought it was pretty cool.
Oh, I guess when I was a kid, I started reading comics at the barber shop. And I was an old school kid back then, you know, Superman and Batman, Flash, Green Lantern. And I saw the Marvel books and I thought, wow, these are weird. And I kind of took an interest in some of them. I was never really big on them. My brother and I, we were huge Conan the Barbarian fans. We read everything that Robert E. Howard ever wrote about him. And then when the Conan comic books came out, I started reading them. And
okay.
And then it would have been, I think it was late 70s. For some reason, I took a notice to the Warlock comics. And he was sort of a philosophical anti-hero type.
I sort of remember that.
Yeah, he was. He had kind of yellow or gold skin. If you remember the people in the second Guardians of the Galaxy movies that the Guardians were fighting. They were tall and skinny, and they all had gold skin, kind of yellow.
Don't remember.
Um,
By the way, I saved a little Rosette. We're going to move on to a dark nebula right nearby that I'd like to image.
Hey, James. There's an Aussie right there for you. Whoever was saying we didn't have any Aussies.
Oh, yeah, we got several. Simon Thompson. We got James Dugan, who's here now. Hi, James.
Hello, James.
Yeah.
Anyway, yeah, they're at the opening of the second Guardians movie, where they fought the big giant worm-looking thing. The people there, they had the yellow skin, very hoity-toity.
Okay.
They're coming back for the third one, and evidently the queen of the yellow people, I forget what they're called, she creates Adam Warlock.
Huh.
The guy from the Warlock comics.
Wow. Okay, well, there's a story.
Anyway.
Had no idea. Okay, we're going to go to this dark nebula right here and see if we can image it.
Barnard 174.
Yeah. Also known as Lynn's Dark Nebula 1165. And we'll see these two stars. And that'll help us know where we are. So let's check it out. This is our field of view. If you look at the numbers, you turn your head to the side to see them upright. So it's going vertically. Oh, you can actually see it. It's going right here. You can see this dark nebula in here and now. See it right there? Right there.
Mm.
So let's try 45 seconds on this and see if we can pull this fabulous dark nebula out of the shadows. Probably started a little too soon because I didn't allow my guider to get stabilized. But we are. That's pretty good. We'll see.
You know what? I'm nerding out here, but the one thing I really disliked about the Guardians of the Galaxy movies and then on into the Avengers movies, the character Nebula, that blue girl, she was the sister of what's her face, Peter Quill's first dog girlfriend.
All right.
She was like half humanoid, half robot or something.
Okay.
Oh
wow.
Wow, nice.
Look at this.
She was played by Karen Gillan.
I don't know who that is.
The redhead who played Amy Pond on Doctor Who with Matt Smith.
Okay.
Surely you remember she was a tall, lanky, redheaded girl.
Sorta.
Matt Smith was the doctor, and she had a boyfriend named Rory.
Oh, I remember Rory, yeah.
Yeah, Rory and Amy Pond.
Okay, I remember that. Hold on, guys. I have to go back to 1 second. I'm going to move this up and a little to the left.
Yes, Louis. She was in Jumanji. She's been in a number of movies. Yes, it was the same girl. She played Amy Pond on The Doctor. Well, that was my problem with her playing Nebula in the Marvel movies, was you can't even tell it's her. They got so much makeup and prosthesis slapped on her. She's blue, for one thing. You can't even tell who it is.
She looked like she has like scales. Is that the one?
I wouldn't say scales so much. She looked like she's covered in plates and stuff.
Yeah, okay. I know who you're talking about.
Robot. Yeah, Nebula. One of Thanos' daughters.
Huh. Who would have known?
But somehow, under all that makeup, they managed to cover up a really cute redhead.
All right.
She was evil, too. As Nebula. Sorry, I'll try to turn the nerd off now.
No, it's okay. That's not nerd. That's just geek. That's a little different from nerd. Okay, we're stable here.
Gamora. Thank you, Tara.
See, you're not the only geek.
Yeah.
Okay, we're taking a 45-second exposure here. We're stable in our guiding. And we'll drop out of night vision mode and head into stack mode. So this is the last one. So I move this up and to the left so we'll be able to see more of this here. That's beautiful. That's going to be gorgeous. What about if we just play with that? Oh, look at that. Okay. I'm going to clear it, but it's going to be better in just a sec. Sam S. says, has anyone attempted to digitally rotate the objects? Well, okay, in order to do that, digitally that's easy to do, but to actually rotate the objects and make the camera's long side pick things up, that's not as easy to do. You need what's called an image rotator, and we would have to install it on the telescope to actually rotate the camera 90 degrees one way or the other. I thought about it, and I could make something to do that. But that means I'd have to have the camera somewhat loose on the telescope so that mechanism is the only thing that would actually be holding it to the telescope, and the slightest misalignment could cause things to go out of focus. So there might be problems with that, but I thought about it. I know another way to do it too, which could be problematic. Look at this. Is this a red nebula here? Wow. You see that?
I see faint red in there, yeah.
Let's see what else is there. Let's push this. Wow, look at that. Well, this is a beautiful little nebula. Now you see that? This is one of those. This is the thing that these are the most exciting parts of the universe, guys. These dark nebula, this is where it's at. This is where stars are born. This is where planets are born. This is where we were born, in a dark nebula. Ah, look at that! Wow. Yeah, we got some red nebula over here, and we got this here. That's neat. 45 seconds is just long enough to pull that out. I like it. Look at that. Wow.
That's cool.
That's going to make a nice composition when we're done with this. All right. Let me make sure we're still focused here. Okay, we're good. There you go, Izabela. There's another one to start processing, Izabela. Once it's up there. We got this beautiful dark nebula and this beautiful emission nebula, diffuse nebula as we call it. Refuse of the galaxy's processes are these dark nebulae. That's right, Marcin. Faint emission nebula. These aren't stellar nurseries per se. These are just hydrogen clouds that are being ionized. They're not an actual stellar nursery, which is a collection of denser material that forms stars. This is just a drifting clouds of ionized hydrogen. So many stars. Uberku says, yeah, there are. There's stars within stars, it seems. Stars within nebulae, stars within areas. So many stars in a small area. It's crazy. We can zoom in how many stars. Let's go find out. Let's go into this nebula. Okay, we're at 650%. We got 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's endless. And of course, I'll stay here for this next stack to see if some of these color artifacts go away. We'll see it in 3 seconds. 2, 1, 0. Let's watch. Yep, see? Little by little, they're going away. And that's going to bring out the data, that is to say, the dark nebula, the stuff that's real data, versus the noise, which is the stuff in between it all. Wow, that's pretty. I'm sure we could figure out more. There we go. Let's just want to do that. Look at this nebula here. It's so dark. You know? And you might think, well, that's really dense. It's really not. It's only got a few atoms per cubic centimeter. Okay? Whereas we have a hundred million atoms in a cubic centimeter of air. Here we have maybe 30 atoms per cubic centimeter. And here they'd be atoms because it's cool enough for atoms to exist here. Yet down here in this diffuse nebula, it's hot enough by nearby stars are ionizing the hydrogen gas, so any other elements in here might also be ionized. So the temperature is hot here, and it's absolutely cold inside here. The dust grains in here are very, very cool and have ice on them for sure. Those ices can be methanol, carbon monoxide. We have water ice, carbon dioxide ice. There might be some hydrocarbons on there in the ices. And once a star forms, it'll melt all those off and form this slurry of material that could be used for planet building if it gets to that point. We're now starting to see more detail in these other clouds. The subtlety here is amazing.
Yeah.
Seeing light in dark areas. That's something. So let's see if we can adjust and make that actually happen. What does it want to do? Let's try that first. It doesn't change much. But what if we were to move it just a little bit backwards? Too much backwards. Come back in a little. Alright. And then pull it down a little. Look at that. Wow. Definitely have some bright spots out there, don't we?
Uh-huh.
Wow. And there's the color.
Go over to the left just a little bit. Okay.
Okay, so we see dark chunk there, some there. That's a nice little dark nebula right there. That's cool. And this right here, that little curly Q. I forget which one of you said this out there in the chat, but one of you said that if we could show these 1,000 years ago to someone, we'd be accused of witchcraft or something. Marcin Johansson's asking about the Gaia star survey, and I'll talk about that in a minute. So I'm just mentioning because I don't want to forget it. So these beautiful dark nebulae are my hot button. These are the things that really matter, and I think that this is really cool.
Mars and our solar system would be lost in this picture.
Oh, absolutely.
The Gaia is one of the Black Hipparchus is
Yeah.
I guess you would call it astrometry. It was measuring locations of stars.
Well, there's a lot of detail on almost 2 billion stars in our galaxy, and the Gaia survey actually included chemical compositions. It got their radial velocities, their distance, the speed they're moving toward us or away from us. It did spectroscopic data, so we got their spectra. It's very complete. And the thing about it was we got their stellar temperatures, we got colors, masses, ages, and so forth, proper motions, the speed at which they're moving through the universe. And that was for 2 billion stars. That was actually a pretty interesting achievement too. So Gaia managed to give us all that, and I thought that was pretty cool. The other thing too is, and I'm trying to remember, Gaia also, I don't know what instrument in the Gaia survey was able to do this, but they were able to measure something that we knew happened on the sun, okay, and didn't know for sure if it happened with other stars, and turns out it does. And those are called starquakes. So you could actually see that sometimes the sun has ripples moving through its mass of disturbances from inside, okay? Those are called starquakes. Massive stars would get them, and other types of stars would get them as well. And so starquakes were something that were really interesting to see from the Gaia data. But that was, again, 2 billion stars that were cataloged this way. That's amazing. There's a lot of data there to go through. Decades, 100 years of data, 100 years of data at least. Okay, we did 14 right now. This is looking really pretty.
Yeah.
Wow.
Cosmic, why is the software de-rotator for the Altaz mount so difficult? It's easy for an equatorial mount because you don't have to de-rotate. The rotation is eliminated because you're tracking in right ascension only. That is from east to west. You need to de-rotate Altaz mounts if you're imaging to keep that image from rotating in the eyepiece. And it's difficult because the rate of motion in altitude and azimuth changes constantly along both axes depending on where you are pointing in the sky.
Yeah.
How far east or west, how far north or south. The rate of rotation changes constantly.
The rate being tinier the more north you go, and the rate being large by the time you get to the equator.
Well, actually, if you imagine a star transiting the meridian, it is not moving at all in altitude, but it is moving a lot in azimuth. It's moving east to west.
Oh, are you talking Altaz here?
Yes.
Oh, okay, sorry.
And it gets complicated, and you might be surprised at what points you get maximum rotation in one axis compared to the other one, depending on where you point in the sky. It gets rather complicated.
Yeah.
When Meade first started, back when, I'm not sure they even do it anymore, when Meade first came out with some of their really big SET telescopes like the LX200s, but up like the 14-inch or whatever they made that was really big, they only sold them in Altaz form, but they sold it with the de-rotator on the back of the telescope. So to de-rotate the image, so you could build up useful time exposures. I don't know that they do that anymore.
That's a good question. I don't know.
Back when I got my 16-inch Dobsonian, I bought a thing called a Dob driver that kind of cheated the system for tracking in altitude and azimuth, that it wasn't actually computerized, at least to the point that it knew how to break down and crunch the numbers for rotation rates depending on where you were in the sky. But if you got an object in the eyepiece and you followed it for a little bit with the keypad up, down, left, right, you kind of automatically train the mount to follow that object for a while.
Yeah.
But it could not keep it up, and the longer you let it run without fine-tuning it, the worse the pointing would be. That turned out to be a big waste of money on that telescope. It worked, but only sort of. And the real execution on the telescope where it failed was the mechanical parts. The motor drives were fine. The controller was fine. It had 2 stepper drive motors. But, the changes you had to make to the bearings on the telescope and the way that it actually did the driving and the alt and as axes had a lot left to be desired. And the mount wasn't that good beforehand, and it was even worse after I put that on it. It was just a really hinky setup. Some guy came up with it out in his garage, I suspect.
Well, it worked.
Sort of.
Marcin says that this contrast is really nice, I believe, and yeah, it is. This curlicue right here is really interesting to me. Okay, it moves around like this, right? We got this little tiny spot up there, which looks like a gravitationally contracting glob, okay, which is really fascinating. And then down here we have the main body of this. Look at that filament going right there. That is just so cool. And then we've got this main body here. So this is a very interesting location in the sky. I didn't know what to expect when we went here tonight, guys. I just thought it would be an interesting dark nebula. Turns out it's not just interesting, it's fascinating. You know? Because I love dark nebula. Give me back my telescope for a sec. Okay. Wow. Very cool. I really like that.
Ronald, to try to answer your question, you got an Altaz version of the Celestron single arm mount, and then you added an equatorial wedge. Once you have the telescope polar aligned, the wedge polar aligned, and the telescope, it should track right along.
Yep. Because you have one axis aligned with the basically the central axis of the Earth rotation. So all you have to do is have one axis which follows along east to west, and that's all you need. And the thing is, though, if you're taking photographs, then what you do is you have to guide on the photo to make sure that it doesn't go and drift, because most mounts, most systems do have a drift involved. So does this one. This one has a drift, but it's counteracted by this telescope that you see right here on the back of the telescope. That's a second telescope on top of the main scope. And its job is to guide the shots. So I don't have to. Otherwise, I'd be doing that down in the corner. You wouldn't be able to see me. I wouldn't be talking because I'd be having to guide the whole time. Louis Toss says that condensing of the dark clouds, I imagine you're talking about this guy here, looks like the beginning of a baby star formation. Well, it could be. Absolutely. That's where stars are born, in those dark clouds. Then when they come out, they start to ionize gas nearby like hydrogen. Hang on, I gotta get something to drink. I'll be right back. Sorry.
Sam S. had a question. Is it possible to rotate an object with software so that it appears three-dimensional? Yes, it is. There are examples of this out there, YouTube, etc. NASA, others have done it, where like they are taking a three-dimensional look at the Orion Nebula, for instance, M42, and some other popular objects, that they actually rotate it through 3 dimensions, and they actually fly you right through it. It's going to take a heck of a lot of computing power to do it, and a lot of position data, and accurate modeling of the actual three-dimensional shape of the nebula.
Oh, is he talking about making a 3D model?
He asked if it was possible to rotate an object with software
Okay.
so that it appears three-dimensional.
Yeah, that was an earlier question. That's right.
Yeah, I think he asked it the first time.
Yep. Okay, let me check right now. Let's check our view here. We're right around here. And I want to see if we got any clouds that have come in since then. And the answer is no. All right. Even fewer. See that? Nice. Okay. Oh, look at that. This looks like a beautiful composition, doesn't it? I mean, it looks like a piece of art. At least to me it does.
Mark, I'll be right back. I gotta go find a book from Martin.
Okay. No, we have no clouds up there, Uberku. We're fine. Oh, Izabela, there's so much we can do to make this even better. She says, this image doesn't need processing. It's perfect. Yeah, we could use some. Let me try this here. Okay. Alright. Oh, what the heck? Oh. Let me minimize that. We don't need it in the way here.
Okay, back.
Okay.
Martian, the name of the book is Mythology. The author's name is Edith Hamilton. And the name of the artist who did the cool illustrations.
What was he asking about?
He was asking me about the name of a book of mythology that I had mentioned in the past.
Okay.
Mythology by Edith Hamilton. The illustrations are by Steele Savage. STEELESAVAGE. Steele Savage.
Wow.
I read this book when I was a little kid. I wrote a book report about it. I found it in the back bedroom closet that all my older brothers and sisters kept their books in. I was blown away by the book and by the illustrations by Steele Savage. I wrote a book report about it, turned it in, and the teacher accused me of having my older brothers or sisters writing their book report. She didn't think a fourth grader would be reading something like that. But I did, and of all things, years ago, I was at a yard sale one day, and there was a bunch of books on a table, and one book cover just jumped out at me. I recognized it from across the yard. It was the cover of this book. It shows Perseus holding the Gorgon's head upraised in his left hand while he's holding a sword in his right hand, and he's wearing his magic helmet. There you go. And I bought that book right then and there, and I still have it to this day. Actually, it was sitting on the headboard of my bed when you asked the question, so I went and got it. It's a great book. The illustrations will knock your socks off too. Just here, I'll type this.
There you go. That's better. Okay, we're going to pause this here. This is 31. We're going to save it. save it exactly as seen. All right, and once again, this is Barnard 174, one of the dark nebulae that E.E. Barnard had cataloged. All right, so that's this guy right here. There you go.
Sorry to go on like that.
Before, that's fine.
He managed to push one of my buttons.
It's okay.
I love this book. And I've had it, many years ago. I found it at a yard sale. I mean, it just called out to me. And I snapped it up. The book is disintegrating, but I still have it.
Do you have star lore? Their star names, their lore and meaning?
As a book, no. I have links to websites that talk about star names, their lore and meaning.
Okay. All right.
And pronunciation guide.
All right. So this is done here. So I saved it. I'll save it one more time. Save it exactly as seen. And then we'll be done with this object, even though I saved it already. All right, that's very cool. And we'll clear it next time we come in. So let's get out of the stack and go to a 1 second shot for our hyperstar shot, night vision scene. Okay, now based on this, let's see where we want to go from here. That's a great deal of fun. All right. All right, so we're going to go there now. This is a cool star. So I'll show this star just before we go elsewhere. This is Arrakis, otherwise known as Mu Cephei. This is Herschel's Garnet Star. It's a red supergiant in the constellation Cepheus. Here it is. Its surface temperature is about 3,600 Kelvin. It's almost 20 times the mass of our sun. And it really is a stunning star. Let's move it over. Oops, I went the wrong way. Can't believe I did the wrong way. I knew which way to go and didn't even bother. Okay, so we're going to move over now. Okay. It's 283,000 times the sun's luminosity, so it's actually quite bright. It's a red supergiant, as I said. And it's destined for a supernova ending. It's like a M1 or 2, but it's a luminosity class Roman numeral 1A, which means it's a it's a star that is a supergiant, many times the mass of our sun, and will eventually go supernova. Let's do 12 seconds on this and go into a live stack just for fun. We're going right now. 12 seconds is good. So we'll clear this. We'll be back. Okay. And there's the Garnet Star. Let's normalize our curves. Look at that. And you'll notice it's near another nebula, which is where we're going to go next after this. Amazing, huh? Beautiful, beautiful red star. That's really pretty.
As big and bright as it is, I imagine that must be what's lighting up that nebula below it.
Well, I don't think so, because Mu Cephei is actually a very cool star. It's only 3600 Kelvin. So there's not a lot of ultraviolet radiation coming out of that.
Oh, okay. How big was it compared to the sun, what you said a minute ago?
286,000 times luminosity, so it's 20 times the mass of the sun.
So it is really bright.
Yeah, I think there's some emission lines in it too, which I gotta see if I can identify. 269,000 times the luminosity of the sun, you know, depending on where you look. Okay. It's also nearing its death, without a doubt. It's going to be going supernova. It's right now. It's gone up the asymptotic giant branch. It's burning, infusing helium into carbon, and so after it does that, it'll fuse more elements, possibly at 20 times the mass. It can actually create all the way up to iron in its core. And after it goes supernova, because of its mass, it'll likely the remainder will likely become a black hole.
Ronald, that is an interesting question. Ronald asks if this star would have a green zone, and we clarified, and he's talking about the habitable zone.
Oh.
Or the Goldilocks zone around the star. I imagine it did before it became a red supergiant and grew so darn big. But who knows? Once it got so big, the habitable zone may have moved farther out into the outskirts of its solar system.
Well, the only problem is, though, at 3,000 Kelvin, the habitable zone would have to be very close. But on the way up to that, it may have expanded well beyond the size, and then this could be we don't know where it is in its size. It could have already gone bigger and then smaller, and we're seeing it now as it was smaller. We don't know. But when the star is like a red supergiant, its original constitution, its composition originally, probably made it a very, very hot star to begin with, especially if it's 20 times the mass. It was probably over a beast type star before it became this. You know what I mean? It would fit those profiles. Yeah, cosmic ray, that's what I mentioned. You're right. And so I think that we would need to have a ionizer nearby. But I want to show some other stars too that are carbon stars, so people can see what they are. I don't know that there are any nearby.
Excuse me. How about about Mira.
Yeah, where's Mira?
That's down in Cetus, isn't it?
Yeah, it's other side of the sky.
Oh, well, never mind.
Let's find out here. I know I spent a good share of my time looking at these. The carbon stars are extremely red. They almost look crimson. They're really amazing.
Yeah.
Well, there's some in Hydra, some in Taurus. Oh, I love them. They're just beautiful. They're probably one of my favorite colors, of the star. But anyway, okay, so we'll just we'll save this. Why not? The guiding is so good. We've got him. All right. So we'll pause it. We've got 28 stacked. That's a lot. And who knows? Maybe when we go into the next object, we'll be able to mosaic it with this. We'll find out.
Find a good carbon star?
No, I was thinking of the for the elephant's trunk.
Oh.
What are you doing? What's that? Crunchy, crunchy.
Sorry, it was something that was stuck in the pages of that book.
Oh,
Sorry.
a Tic Tac from 20 years ago.
No, it's
Okay, we're good.
two wood screws or something.
Huh.
Little plastic envelope.
Wow. All right.
No idea where they came from or how they got there.
Okay, we save this. We're gonna be done with this. Okay, and then we'll go back to our night vision mode, so we can move on. There it is. There we go. Now, let's see which way we're gonna go to. We're here right now. Oh, look at that. We might be able to do that if we just drop it down. If we just head directly south, I think that might be kind of cool. So let's do that. So we're going to go directly south here. Because there's a nebula down here we want to see. Alright. And we'll let it search. It takes about 14 seconds to get our guide star, which we will do. You can see the telescope leaning over toward the northwest, sorry. Okay, it's zeroed out and off we go. Let it stabilize for a second. Do 45 seconds here. Okay, we're stable. Off we go. Alright, so now we're just a little south of where this image was taken. And we're going to see this up here now, probably. So we'll be unwittingly making a mosaic of something. What is that something? Aha, you'll see. And it will include Herschel's Garnet Star if we wanted to. Sorry, I left that up there. I meant to say Herschel's Garnet Star there. Well, there we go. And we did it. Okay. And so this is going to be Elephant's Trunk region. To Mission and Dark Nebulae. Let's do an auto view. Look at that. So there's that thing up there I was telling you about. That's nice, huh? And then we'll do it to the right after this. So the Garnet Star is just off the view to the top. And then we'll just be down here. This is the elephant's trunk right here, and it goes off into here, which we're gonna get to shortly. Wait, how are we doing with the did I let that do its thing? Yeah, I guess so. There's some double stars there that look elongated, but most of the others are pointy. The points. That's nice. So we went from the elephant's trunk down to the region known as the Elephant's Trunk Nebula, which is actually a really cool location. Not a place you'd like to be because it's really hot there. Yeah, I missed the conversation too. I have no idea what you're talking about.
That last sect's about Spammer.
Oh.
I hit him and Izabela hit him. Or did
Oh, I see. Gotcha. Okay.
Getting pretty late at night and late in the season for Cygnus Ray. I mean,
we're not in Cygnus now.
He'll be up there for a while. He'll be over fairly low in the northwest even through Christmas, but he is in the decline.
Yeah.
It is in the decline.
Ray, we're in Cepheus right now. We're not in Cygnus. If you notice, here is Cepheus. The elephant's trunk is at the bottom of the house in Cepheus. Okay.
Yeah.
And this is Cygnus here. We're not going to Cygnus. Although we could.
Oh, when you see that chart there, you see Cepheus is pretty much west of the North Pole now.
Yeah.
So he's in the northwestern sky.
Yep.
And then Cygnus is a little bit farther down to the northwest.
Yeah, and if you look where the horizon is,
Yep.
you know, we can't even see Albireo now, down here.
Yep.
And
Saturn is set.
You know, probably wouldn't be able to see Satyr right now either. So let's find out. Let me see here. Yeah, no, we wouldn't be able to see that. We probably do 25 degrees pointing out that corner. But part of this building would block it. We could probably see some of the North American nebula, but yeah, we're not into Cygnus tonight. We're just up here. It won't be long before the elephant's trunk is going to start to impinge on the back of the building too.
Yeah. Mark, could you back out in Stellarium a little bit for a moment? Yes, folks, when you see that now, the Milky Way from back in the summer, all the way down to Sagittarius, that's all set now. And the Milky Way is continuing up through Cygnus and up through the northern sky and crossing over into the winter sky there by Cepheus, Cassiopeia, and Perseus, and going down into Auriga and Gemini, or Auriga and Gemini, and
then Orion. Yeah, so the Milky Way is year-round. It's just a different spiral arm we're looking at. which is cool. The only time we don't see a whole lot of it is in the spring sky. But then it's galaxy season. Rabbit season. Duck season. Rabbit season. Okay.
Excuse me again, please.
Sure. Okay, so we're doing this exposure. We've got 10 stacked here. I think that's good for this right now. So we'll pause it and save it. Not yet, I won't. I'll just come up here first. And this is the elephant's trunk region. So we'll do that. Now we can say that. Save. Save exactly as seen. Okay. Then come out of the stack. Move us over just enough. Get into our 1 second shot here. And put us into this mode. And now we can move us over a little bit. So we're going to move a little to the west now. Excuse me. I think I should be able to avoid the COVID running rampant in my house. Although I seem like I'd be a ghost right now. Okay. A little more. Okay. Okay, a little more there. And then we'll have be in the right place. Okay, there we go. Okay. All right. And now we'll do 45 seconds. All right. 45 seconds there. We're guiding all set, and off we go. So we move this over significantly. This here is now there, so we'll catch the other side. And we're still in the elephant's trunk region. So we're going to clear this now. And we'll see the rest. Okay, so the object ID that we had there is still valid. Izabela, I just came out of the bulk, that's correct. There we go. There's the other side. And it will have the upper part of it as well. Is Tim F here? Or just Tim? Hey Tim. How you doing? Hey Tim, welcome to the channel. It's live astronomy, deep sky. This is live. This is actually the first image we took. You'll see the second one now. Alright. Boom, and the image starts to get a little clearer with each time we stack a new image. And I'll take that out of there. We don't need that. We know what it is. This is the elephant's trunk right here. You can see the elephant's trunk. Yeah. Hello, Daryl.
Hello.
Tim says, hi, what telescope is used? Well, we actually have this telescope right here that you see right there. I know it's small. That's a 10-inch telescope with a guide star telescope on top of it out in the Arizona desert. I'm actually in Connecticut, so I'm 2,500 miles from our telescope. But we're doing this all remotely. And the telescope is normally runs at a speed, a photographic speed of f8. But we added a system to allow us to run the telescope at f2, which makes it a telescope which delivers a 4 full moons across field by a 3 full moons tall. So just over 2 degrees and just over 1.5 degrees in size. So we do these beautiful wide angle shots of the night sky. However, the telescope camera that we're using supports us being able to zoom in and see details at a much closer level. So this allows us to do that too. We can get even closer. As we stack more images, the noise that is around this, that occurs in the spaces around the stars and around the nebulae is averaged out. And all the data comes to the top and the noise goes down and is suppressed. So that is helpful. Let's see where it wants to be. Oh yeah, look at that. That's really pretty. That's really pretty.
Have you increased your exposure times?
It's 45 seconds.
I know you and Izabela were talking about that the other day.
Yeah. I am doing 45 seconds, which is more than we usually do, 20 to 25 to 30. I'm doing 45 seconds just to go over the top and get that little extra bit of data. You're welcome, Tim. Tim says, very cool. Thanks for the info. Technology and all has gotten so much better. Yes, it has. Yes, it has. And also, Tim, our observatory out in the middle of the desert is fully green. All of our power is delivered by solar panels that are on the site. And our internet is from Starlink. It was previously HughesNet and Viasat. But we got rid of those in lieu of Starlink doing so much better. And by the way, Tim, all the data you see here it goes up to a server where you can get at this data and enjoy it. To get there, just go here, SkyTourLive.com, right below. There it is, SkyTourLive.com. You scroll down and you'll see here, take me to wonderful data. There's a blog now, and just below the blog you'll see take me to get good photographs, and then you just double click on the folders until you see one called processed, and in there you'll see photographs, these photographs, and you can download those and use them and enjoy them. Hello, Laura Newbert, how are you? I haven't seen you in a while. I hope everything is all right with you. How are you doing? You're welcome, Tim. Make sure you subscribe, Tim. Subscribe, become one of the, it's all free, and become one of the SkyTour LiveStream family. Got a lot of people here that enjoy this stuff. Laura says, all really good, just very busy. That's good. That's good, Laura. I haven't seen you in years now. I mean, I saw Laura out at the Devil's Tower UFO conference 2 years in a row. But haven't seen her, but that'll be alright. Thank you, Tim. Tim subbed and thumbed up. Thanks, man. I and you together, let's break your telescope? What? What are you talking about? What's Izabela saying?
I don't know.
I don't know either.
Sounds subversive.
She's having a Bulgarian revolutionary moment. Hey, Bullwinkle. Oh, Ronald, how many years have you seen me at Pine Bush? Is that what you're asking? Wow. This has to be, what, 5th or 6th year anyway, right? Ronald? Let me tell you a little bit about Ronald. Ronald gets in his car from Minnesota and drives 22 hours to get out to New York State to a conference, a little conference that's called the Pine Bush UFO Fair every year. And he comes to see me speak and the other people that are speaking there. And then he drives all the way back. That's going to be a lousy ride back, knowing that, you were going because you anticipate the fun at Pine Bush. But then when it's over, it's like, oh, I got to drive home now. But he does. He does a wonderful job. And I have to say, he's one of the most faithful guys there are when it comes to people that, like what we do. All right, there's 10. All right, we're going to pause it here. Save it again as Elephant Trunk region. And save exactly as seen. Okay. We're going to stop this stack and we're going to go up to a little higher and grab the other part of this one, the final piece. So we did 1, 2, 3, and we'll do 4. Here we go. Okay, 1 second. Imagery. Oh, there we go. I was missing it. How about that? There we are. And we go to the green screen, to our night vision mode. And now we go up. And that should take us. And there's the Garnet Star up there. And I think that's about good, maybe a little higher. Yes, because the Garnet Star was centered in the view. So there we go. We'll put it right about here. And then we'll do 10 here. And then we'll get the picture of the entire nebula. And before we even get done, I guarantee you Izabela's going to go up and do a composition of the whole area. If I wasn't doing this, I would. Okay, so we're going to do another 45 seconds. We're guiding again. All right. Our guider is stabilized, and off we go. So now let's go into our live stack. and you'll see the previous data. This is where we were, and what we've done is now brought this all down, and the Garnet Star, which is out of view up here, is now down here. So we're doing this upper right quadrant. We did 1, 2, 3, now 4. We'll have 4 done. All right, and I gotta clear this so we can get ready for the next one. This doesn't overwrite anything. This is the buffer. The sensor is gaining all the data. All the photons are hitting the sensor, and when they get read out, that's when they could collide with what's out in the display buffer. But here, as you'll watch, you'll see. So this is the upper part of it now. There we go. Yeah, we'll let you see how. See, that's the upper part. That's pretty cool. So this will make a nice 4-panel mosaic.
I guess I didn't realize the Garnet Star was so close.
Yeah, it's true. Herschel's Garnet Star.
Yeah.
Yeah.
Herschel out around.
Yeah.
And his sister and his son. Actually, his son got around more than any of them. He did a lot of observations from South Africa. He helped pioneer the southern skies.
Oh, that's cool. Yeah. So, James Dugan says he likes these stars right here. These 3 little guys right there lined up like an exclamation mark. Ray
I
asks,
see star trains in this image.
mm-hmm.
As ever, you wonder if they're real or if they're just line of sight.
Yeah.
Some of them just look too regular, though. Some of those curved lines, especially over in the upper left-hand quadrant.
Yeah. Ray asked a question about camera, actually a sensor. The Sony IMX585, better image sensor, square pixels. Yeah, I mean, the pixels are a little smaller than this camera's pixels, so we'd be able to zoom in more. And you'd have to get used to a square format, which is kind of what we're almost got here. If I was to shrink this down a little, we could actually make us look what looks like a square format. But this really isn't the square format, because if we actually zoom out to where it should be, all right, autofill, okay, you'll see it's a rectangular format. So this is 4 full moons across and 3 full moons tall. All right, so that's what Ray, Cosmic Ray, is asking about, is that concern or that thought process about which camera would be better. I'm thinking about going to the smaller pixels, Ray, so that we can take a hyperstarred system and zoom in a lot more on objects, you know.
Do you know how many, what's your pixel to arc ratios? What your pixel to arc second ratio is?
Yeah, I actually have it in Photoshop because I use that to calculate distances on the plate, arc distances. Let's see. We have 4,144 by 2822, 2,822 pixels, and the size of the image of 2 degrees roughly divided by or 4144 divided by the 2 degrees will give you that value in the horizontal, and then we could do the same thing for the vertical axis to figure out the rectangular coverage. I just to go through this again.
4144 divided by 7,200 then?
Probably.
2 degrees?
Yeah.
Okay, Izabela. Marc, Izabela says for a full panorama, you need 2 more images north and 2 more down south. You have the middle of it now.
Well, I started up here. I just had this over here.
Don't argue with Izabela.
No, I'm not arguing with anybody. I'm saying this was here, so I started there. I think, if anything, I need more southern shots. 2 inches north and 2 more down south. I'm not sure what she means. It wasn't my intent to do a panorama at all, but I figured while I'm here, while we're doing it. Isabel, show me the picture. Show me the composition.
She's going to show me the picture.
She didn't show you?
Well, she said she's going to send them to me.
Okay.
I guess you done made her mad.
I didn't make her mad.
She does this. She'll send them to me and I'll forward them to you.
Yeah, just stick them in the chat.
Oh, no, I was wondering about the arc seconds per pixel or whatever ratio. I saw somewhere recently they said ideally you want somewhere between 1 and 2 pixels per arc second.
Yeah, I saw that when I was getting all this equipment, spec'd out. I just felt that I didn't know what to expect with the Hyperstar really, and how well it would work. So it works better than I thought it would. It's really quite a nice system. Anytime you add lenses to a system, you think about losing some resolution a little bit, But we're actually removing the secondary and going right to the camera through the lenses, so that works pretty well. Okay, we have one more to go here for the 10th one. Actually, we're on that final exposure now. And there we go. So we'll save it and wait for Isabela's comments so we know which way to go.
I can't get it to move over. I got one of them already, but
well, is it in our dual chat in Skype that we did?
Yes.
Well, let's go there, shall we? Maybe it's there.
Yeah, it's there.
Okay. So
I was trying to drag it over to your chat, and I can't get it to go tonight.
Okay.
I've done it before.
Okay.
Alright, let's see. I'll open it, and okay, there's that, and then back to...
Alright, so let's go to that other chat.
I'm lost all of a sudden.
Okay, I got it.
Okay. There it is.
She didn't get the
She said this is the first one.
Oh, is there another one coming?
I guess.
Okay, well, I'm looking in that chat too. Bear with me, guys. We're just trying to see if we need to take some more images here. Because I don't see this star in any of them. So there's 2 more at the top that should have been included.
Ray, I'm not sure that's really a true statement. The scope out there is essentially a RASA. The scope out there is an analog of what's called the fast star system, which is a brand name owned by Celestron. It's a F2 conversion. The RASA is a Rowe Ackerman Schmidt astrograph. It's a little more specialized. It's a little more to it than the so-called fast star or hyperstar system.
Yeah,
it's a Schmidt camera.
I just looked at this and I noticed something really strange. All of a sudden, looking here, I see like a line going right down through here.
Yeah.
Isn't that weird? A line right there. Never saw that before.
Line of stars?
Dark nebula and everything kind of draw like a line. It's really strange. Holy cow.
Yeah, I think the dark line is like, I call it spiral eggs sometimes that I see.
Yeah, I just was looking at something else. I looked back at it and I was like, oh my gosh, look at that beautiful line right there. Yeah. All right. Okay, so Izabela, there's 2 more images. Okay, top right just came in. Okay, so she's okay, she's getting the rest of them. Because I have, okay, this one here is in, and then we had one where this star was in the middle, so that would complete the matrix mosaic that I wanted to do. So we have everything we need there, I think. Okay, so we're going to clear this out and dump the stack. Go to our night vision mode. Check things out and see what's next. I know, Ray. Let's go to Cygnus. Oh, wait. There's nothing actually to see in Cygnus tonight because it's too low. Let's back out of this and see what else we can see. There's so many nebulae up here. Yes, we have the Wizard Nebula. We did that before. Oh, I know what we're doing tonight. Yes. Yes.
Cave.
Yes, we're gonna go caving. We're gonna spelunk tonight. We're going spelunking.
Okay, the second was up over at your other page.
Oh yeah, I could see that we could have used another one up there. Ah, okay. I should probably just do that because we're there. We should probably do it. Oh, but the Lion Nebula. Oh, I want to do the Lion. Okay, here's what I'm gonna do. Okay, I'm gonna go back to Herschel's Garnet Star, and I am going to make sure that we actually get the final image. Let me just show people what I'm talking about. So let's do that. First things first. No, wait a minute. There's another one still, Izabela. There's another one you should be getting. There's another one. You have 3 in there. You don't have 4. Okay. I can actually just do just to show Izabela. I could do this. Okay. Like that. Get it to there. And then go north a little bit. Okay. This is a shot I don't have, that's for sure.
Fill that top left corner.
Yeah. So this'll do a bit of it. Allow us to crop a little.
I wonder if he forgot to save it, Izabela.
No way.
Ah.
It was the first one. I don't think I forgot. I wouldn't put it past me, but I don't think I did.
Senior moment.
Do I look like a senior? Don't answer that. Okay. So I think this will fill it out nicely. This will be perfect. And we're guiding fine. 45 seconds underway. Then we're going to go to the Lion Nebula, and you guys are going to love that. Oh my gosh. The Lion Nebula. Remember that, Daryl? Beautiful reflection nebula and nebulous detail. Oh, yeah. Had green. You remember it was green and red.
Oh, yes.
Yeah, and I think it's really blue and red. I'm not sure. Yeah, we're going to get to the Lion Nebula, too.
I remember the green and red one.
Yeah, that's the one we're going to see. After this one. You want to see a spectacular nebula, guys. It looks like an artwork. And that's what we're going to do after we do this final one here. Alright, so there is the rest of this. This is what's left for that image over here. We have to fill in.
Nice star field.
Mm-hmm. Look at that.
And more dark nebulosity.
Yeah. I'd love to do, you know, if there was a way.
What? Did you clear that?
What? This is the new image.
Oh, I thought I saw you hit the clear button.
Oh, no. No, it's still going.
Okay.
See, we've got one stacked and the second one's about to come in.
All right.
Watch, it'll say 2 now. There we go.
Are you trying to get the same number of exposures for each of the panels?
Yeah, just so that they have the same rough brightness, sky brightness, so it's less of a hassle to get that sky brightness. And the reason I went back to it is because you need to do it on the same night as best you can. Otherwise, you get different sky brightnesses sometimes depending on what's going on in the sky. If you have more water vapor in the sky, you might have a haze that you didn't have the night before. So if you're going to do it all at once. This is really a beautiful area. But we'll actually have some fun with this. Alright. So we've got 3 stacked now. That's good. Okay.
Izabela, it's down at the lower edge, right-hand side. Might be kind of hard to read.
I'll show you, Izabela. This is the frame location right here. For those of you watching, make sure you're on 1080p. The other place to see it is here. Frame stacked right there. But when I'm letting people see the whole screen, this is what you see. And then we just get rid of this, pull this over, pull out the blinds, and check it out. Wow.
I still find it hard to believe that red nebulosity is not coming from the red light from that red star. I understand what you said about, you know, the
Ionization potential. Yeah.
I'm sorry.
Ionization potential.
Yeah, I mean it's putting out low energy light, not ultraviolet. But sure, just looks like it's lighting it up.
Yeah, it does. One of the universe's great illusions.
Maybe it's like sunset light. Even though, you know, you got Rayleigh scattering, you still get red sunset light. in Earth's atmosphere.
Yeah, but the star would be red for reasons of dust extinction and, you know, scattering of blue light from the star, but this star doesn't have much of it. There's very, very little blue light from this star at all. But you don't see the bar now, Izabela, actually, because I'm in this full mode. But if I give you back the telescope and move that over and show you the telescope, now the bar is right here. You can see that's small writing, no doubt. I maximize the screen with stuff we want to see.
Seeing the telescope view, you are pretty far in the west.
Yeah. That's why I want to do the line as quick as possible, and that's we're closing in on 8 frames.
How many are you shooting for?
10.
Okay.
And that should be fine. And once you're within 2 frames like we are right now, I mean, you might as well just wait the 2 frames. It's just another 90 seconds. Looks nice. We got some dark nebula down here. Look at that. This dark nebula here. We'll be able to separate that in processing. The more data you get, the more detail in this you get, because it's rising to the surface in the stack. Subtlety.
Izabela has a question.
Yeah, I see. Memory, 4 of 5 frames in use.
Oh,
4 of 45 frames
Yeah,
in use.
it's right there, just left of the center at the bottom.
Yeah. Not sure about that particular parameter. So I don't know about that, Izabela. I don't know what that parameter really means.
Oh my god.
I studied and looked at only the things that I really need to know. And I learned about the intricacies of how it gets to things like plate solving to figure out where it is in the sky. Cosmic Ray says, any voids out there that you could image? Yeah, well, the last one we just did, that Barnard object we just looked at, was it Barnard 174? That looks like a black curly Q. Here's a void here. Okay, there's a void here, but these aren't voids. This is a dark nebula, out there, so that's pretty cool. And we're at 10 frames. Okay, we're gonna pause and save it. Okay, Izabela, when this one comes in, you'll have that last piece of the puzzle. Alright, we're gonna clear this now.
Would you call that little window we see in the Iris Nebula, would you call that a void?
I guess it is definitely a true void in the dark nebula that allows you to see the other stars in the background, yes.
Yeah.
It's like seeing my fingers through my other fingers are up close. When you see these fingers, you're seeing them through a void between my fingers, right? The same way we have that going on with the Iris Nebula, like you said. And that's how that works. Okay, save exactly.
Otherwise, I mean, what comes to mind when I see the word void?
Lack of.
Yeah. Well, the Boötes void.
Yeah.
Had people ask about. That's in the spring sky, but I wouldn't know the Boötes void if I saw it.
I think because you can't. That's the whole point.
Yeah.
Okay. And now, let's go check out the beautiful Lion Nebula. The Lion Nebula is right up here. Right there. I actually stumbled upon this nebula the other day, and I just couldn't believe how beautiful it looked.
Well, that one too, it's setting now. You see it's in decline. It's, I mean, looking at the line of declination, I guess it is, they're coming from upper right to lower left. It's lower than Polaris is, lower than the North Pole.
Yeah. I never saw the altazimuth lines in there. I'll get rid of them. Alright, so right here is the Lion Nebula. But what we want to see, we want to make sure that we see what's really going on in there. And to see that, we've got to move a little bit west and then a little bit south. Because there's something else that is actually down on the lower right here that really makes this thing stunning. Alright. And why it's called the Lion Nebula? I don't know. Okay, this is good. And then this is that'll be too much. I'll probably have to come back a little. So right there, I think is good. And just head north again for a second. Just a little bit. Oh yeah. Maybe one more jog. Alright. Now we'll catch our guide star. We gotta wait 13-14 seconds. Ray, I don't you say void as dark nebula. Yeah, there's other dark nebula out there. I actually activated the Barnard catalog in our view. Okay, we are guiding and waiting for our numbers to stabilize. There we go. Okay, we're stable.
True voids are pretty rare.
True.
That was the whole point of the Barnard catalog. Was they used to see dark spots in space. They called them voids, and Barnard, who was a pioneer of astrophotography back in the late 1800s, he went out and started taking pictures, and he showed that they're not voids, actually, they're dark nebula.
Yeah. Will you all excuse me for 2 minutes? I'll be right back.
Sure.
Thank you. I shall return.
C and D boy, the Eskimo Nebula, aka the Clown Face, or the Lion Nebula, or Caldwell 39. Yeah, that is a different object. It is, and Marc's gone. It's more of a, I want to say it's in Gemini, over on the other side of the North Pole. It looks like an Eskimo face, like he's wearing his fur parka, you know. It's got the fur lining around it, his face. And you can imagine it looking like a clown face or a lion too. Okay, you're talking true voids, which are a relatively rare thing. I think the so-called Bootes void is an example. I'm not sure I've ever seen it. And it looks like the other picture is up.
Never fails to disappoint.
Yeah, Marc, Izabela put up another image.
Okay.
The final with the last addition to the mosaic you were building.
Okay.
It's up in your joint chat.
All right.
And that adds nicely to it.
Yeah. Okay. We'll get this to you guys. I mean, if you really want to, I mean, if I want to use like a, was it Sequence Generator Pro or something, I could build perfect mosaics, but then you just gotta, it takes all the fun out of it.
Yes, I just saw it, Izabela.
That's beautiful, Izabela. Thank you. Let me do this. Do this. All right, guys. I'm going to show you what we're doing here. Okay, this is what we just took a picture of right here. So there's the elephant's trunk here, and we did a little this way, and we did up here. We did the Garnet Star, and of this environment up here. It sort of looks like the Hubble Space Telescope. It does little pieces, right, like this. So you can see all this detail up here. Yes, we could have finished this out, and then you'll see, but wait, maybe a little more. And we could have done down below, but we could do that at some other point. There's really no problem with that. I want to do that earlier in the evening anyway. But anyway, back to our matter at hand. Thank you, Izabela, for all that.
Thank you, Izabela.
Okay, and this is the Lion Nebula now. I don't know why they call it the Lion, but I will look up its actual designation after I check focus here. A lot of stars in this one. We have one stacked image. That's it? There's gotta be more than one? What's going on here? Uh-oh. We ignored 4 frames, so we're not stacking right. Why is that? Okay, let's try. We got to clear it. I'm not sure what happened there. It could very well have too many stars. I may have to move it.
See, it says 1 of 45 frames in use.
Yeah. So here's going to be the 1 frame. And it's going to look like what we saw. And now when it goes to stack, it may actually have a problem stacking. It's a beautiful nebula. And what I do here doesn't matter. Shoot, it ignored it again. It's ignoring the frames when I try to stack these.
Wonder what's going on.
I don't know. I'll try one more thing. I'm going to try make it a 35-second shot. I wonder if there might be something strange going on. Alright, so we're going to do 35 seconds. And we'll clear this. Izabela, at first I thought it was 03 because there's actually 2 Wolf-Rayet stars here that create these 2 nebulae, I believe. So I have to figure out which one it may be. Either a reflection nebula, okay, or a O3 region, like Thor's helmet. Cosmic Ray says, do I have a software doohickey to take out the artifact around the bright star? You mean like the halo? I can remove the halos, yes. Let's see now. Okay, see, that's stacked. What is it about 45 seconds that it didn't like? Alright, well, we'll stack it at 35. It might have been a collision between a high gain of 400 and a high time with a lot of stars. They might all run together for the algorithm. So these two stack, so maybe we'll get a third stack here. Yeah, okay. That's going to work. See, we stacked 3 now. None have been ignored. All right.
Does that pertain to what I asked you about if you increased exposure time, maybe you should turn down the gain?
Good question. I don't know about in this case. I was thinking about mitigating noise, right? But maybe.
I don't know. The guys who take stacked 5-minute exposures, what kind of gain do they run?
I think they're around 300 on this type of camera. 300, 350. But okay, I don't know that they have the ability to remove the noise like we can do. I think they probably do. You know, we're really not special in that regard.
I see some very distinct spider legs in there.
Yeah.
There's one just a little below right of center.
Yeah.
And several to the lower left of center. And a bunch more down toward the bottom of the image. I assume there's something real.
Yeah. The Lion Nebula is also, by the way, known as, this is Sharpless 132. And I'll tell you this, okay? I think if there's 2 Wolf-Rayet stars here, I'm going to say that this is probably ionized oxygen and not a reflection nebula. I don't think that's... I don't think that would be a reflection nebula if you got a Wolf-Rayet star here. Especially if you've got the hydrogen envelope that's expanded and the oxygen envelope. So I have to find out where the 2 Wolf-Rayet stars are.
I would wonder... I mean, there aren't that many Wolf-Rayet stars. You would have 2 so close together in space, or in the sky.
Yeah. But there are.
Anything's possible, I guess.
Yeah, there are.
Izabela has a question of you.
Okay. Izabela says, can lower exposure but a lot of still images compensate for a high exposure but less number of images? Okay, read that again. Can a lower exposure, a shorter exposure, but a lot of still images compensate for a high exposure but less number of images? That's interesting. Okay, first of all, a lower exposure will not capture as much data. So you can stack as many as you want. But if there's a faint object that you can't see because you're not exposing long enough, you're still not going to see it no matter how many shots you take. So the idea is to take as many shots with a large enough exposure to capture the faintest detail, all right? So, like, for an object like this, when I came in the first time, I took a variety of shots of it. I took a 12-second, 20-second, 30-second. I found that 35 was reasonable, and 45 actually caused problems. And I think because there were too many stars, it couldn't actually find a pattern to match. And that could have been related to the gain of 400. The stars might have been too bloated for it. But without a gain of 400, we wouldn't have seen the detail. So there's a trade-off you have to make, Izabela. And I think I settled on 35 seconds last time as well. To be honest, I think that's what I did. Eskimo Nebula.
Yeah. C&D or somebody asked it a few minutes ago. Bowman just brought it up again. I guess they did a search for Lion Nebula, and whoever it was asked. It was while you were gone a little while ago.
Okay.
He referred to it as the Eskimo, the Lion, the Clown Face Nebula.
That's not this. Yeah.
In Gemini.
Okay.
And that's the classic Eskimo Nebula.
Right.
Which we have looked at before. That's clean on the other side of the North Pole from where we are.
Yeah, it is. And
on the east side. We're on the west side.
This is Sharpless 132, if you want to think of it that way. It's not the Eskimo. And the Eskimo is a planetary nebula. This is not a planetary nebula.
Yeah.
This is the result of a couple of Wolf-Rayet stars that have blown off their hydrogen envelopes and everything inside those envelopes, including what may be oxygen. And if you notice right here, this edge, it starts this blending between material. There's looks like a hydrogen filament type thing here, and what could be the O3, the doubly ionized oxygen here. So I think that's what's going on here. Do I have any proof of that? It's actually been notoriously hard to find information about this object in reality, but I will figure it out. This is really nice, though. Look at that. A ton of stars in this view. I'd say there's a Wolf-Rayet star right in here. Okay, and a Wolf-Rayet star right in here. That's what I think is going on here. I actually see a cavity in here. I see a cavity in here. So is there one here, one here? And that becomes a question. Why two? This and more information on the 11 o'clock report. That's kind of what this music sounds like. Which you can't hear, Daryl.
Oh, well.
I know, right?
We've been going for 4.5 hours.
We have not.
We have too.
Wow, it's almost 1 a.m. Is that your way of saying you're getting tired?
Yeah.
Okay.
Maybe the classic just one more after this.
Or this is the one more. Unless you want to go check this out while this is exposing. What else would you like to see?
The Eskimo?
Oh, can we do the Eskimo?
I don't know. Can we?
Let's find
Gemini
out.
should be up now.
Let's go find out. There's Ursa Major coming up. There's the Beehive. Gemini is pretty high, and the Eskimo's up here, isn't it?
It's in Gemini. I forget where.
I think it's up here somewhere. Let's go see.
There's Alhina.
Yeah.
It's the foot of Procyon.
Yeah. There's a nebula right here. That's not it, though. What nebula was this? We saw this. The Christmas tree cluster. There we are. Wow, it's that time again. Hubble's Variable Nebula, everybody. Okay, that's strange. All right. All right, so we'll do a search. I thought it was up there. The Eskimo show's nice, if I recall. The owl show's nice too, but that's in Ursa Major. We can't see that yet. Okay, we're down a little bit. 35. That might be close. You can try it. We can try it and see what happens.
Remember,
This is beautiful.
yeah.
Okay.
I saw the Eskimo one time, long time ago.
Okay.
That guy in the astronomy club that had the weird, funky, homemade 13-inch Dobsonian.
Oh yeah.
He looked at the Eskimo with that telescope. I want to say he said he had it running at 800 power, which is crazy magnification, but
Yeah.
darned if that they didn't pull it out. Who knows?
Okay.
It may be small. You need more focal length.
Yeah. All right, we're going to pause this. And this is the Lion Nebula, Sharpless 132. And we will save it just like you see it. Okay. And then we will save exactly as seen. All right. So there we go. So this has a lot of really interesting details in it.
Izabela has a question of you.
Okay, let me get rid of this stack first. Go back to 1 second. Go to our night vision mode. There we go. Alright.
That processed Lion Nebula, that should be in that same queue of images. You were picking your
Oh. That's right, because I showed you
the,
guys. Yeah.
elephant trunk, yeah.
Let's go see. Alright, so let's take a look. Okay.
The green one.
It's not this one. Oh, that's another one you gotta do.
Is it? I don't see it offhand.
I don't either. That's a gorgeous one. I forget what the name of that was. Where did I put it? That's okay. I'll just show people this one too. This one here is another one we're gonna actually, not tonight, but I did this one the other night. 2 versions of it. One of these might be Izabela's. One of them is mine. And this was another one I did. This is the Perseus Cloud, I think. And this is the Northern Trifid Nebula. This is NGC 7822, which we shot earlier.
Yeah.
This is the Iris, with all this gorgeous dark nebula. You can certainly see the separation between it and the background. And,
Cool.
and this is another Northern Trifid shot here. So we have a few to get into and to explore with you, no doubt. And I don't know where that other one went. Did I send it to you?
I thought you did.
I thought I did too.
Well, I don't remember if you sent it to me or if.
Well, maybe
was...
it could actually be in this. In here. Oh, it may not. It may be. It was too large to download, maybe. So it had to come in. Yeah, there's those. Hang on, folks. While we're actually waiting here. We'll just do this. Trying to find something that ain't it. Okay. That ain't it. Oh boy. Alright, I can't find it. So you know what? We'll wait. Let's get back to this. So, where we want to be is at the Eskimo. So we're going to see if it'll go there. Here we go. Big swing of the telescope. Watch the telescope swinging way around here. It's got to go to 38 degrees above the horizon, so it may interfere with the observatory may interfere with it, and we might not be able to see it. Yeah, it's already.
Yeah.
We'll still see stars, but see, we're getting the red of the LED. Yeah, see how low it is?
Oh, well.
That's okay.
We tried.
No, that's
we tried
fair.
the crab for one list object.
All right, let's do that.
Okay. Well, it's higher than Gemini is at any rate.
It should be. All right, and let's go up to Taurus. Taurus. Oh, hold on. Yeah.
Right there. You can see how Mars is moving backwards between the horns of the bull now.
Yeah. Well, we're going to find out here if this is going to work. Yeah, it may. I think we might have just lucked out. Yeah, I think we might have just lucked out. Maybe. Wow. All right, well, I think we just lucked out here, Daryl. Although, I don't see the crab.
Yeah.
If I recall, from this star, it might be up here.
Yeah, up or to the upper left.
There it is.
There it is. To the upper right.
Yeah. Oh, I was at 50%. It would have been in the field if I actually...
Oh.
All right. So I had the field enlarged. Sorry. All right, head to the west. All right, we'll check the focus one last time. Crab Nebula. This is an ancient supernova. Now, we've seen the Veil. And the Veil Nebula is actually not too far away. It's fairly close to us, like about 2,400 light years. And it's 8,000 years old as a supernova remnant, so it's had time to expand. Crab Nebula was in 1054 AD, and you can see that it's fairly compact, but it's also several thousand light years away. So it's actually a lot further away. Okay, so now what we'll do is we got our guiding going, so we're going to go and do... this really only needs about a 25-second exposure, because I don't want to blow out the core. Believe it or not, it used to be the faintest thing I could see with my telescope when I was looking at it as a kid, and I barely saw it. Could never see any of the filamentary structure. But now things have changed. Okay, so let's get out of the Lion Nebula, or Sharpless 132, I think it was. And we're going to go now to the Crab Nebula, and this is Messier 1. The first one in Messier's list. Look at that. Wow. Beautiful. All right. And let's put that out there. You see that? Oh, yeah. And let's color correct. Get our curves aligned. Look at that. We're gonna zoom in on that, Darrow.
Mm-hmm.
Look at all that detail. That's pretty. See, that's why I didn't want to go much further, because if I went more, we wouldn't see the pulsar in the center, but we can. That's the star that's powering this right there. That's a pulsar. That's actually a lighthouse beacons on a dead neutron star. And these lighthouse beacons of high radiation sources are, the star is spinning like this, and it happens to be spinning in our direction. And every time it flashes us, we see that pulse. And it's doing that. This is a star the size of Manhattan Island. And it's rotating so fast that it's going 30 times per second. Okay, that's fast. You know, that's a very, very fast pulsar. But not nearly as fast as the fastest. The fastest one's all over 750 revolutions per second.
Yeah.
Imagine that. Imagine that. Yeah. So let's color correct, and let's actually process. So that's a little more detail there. Got some noise, but again, we're only in 5 stacked images. And we can just pull this down a little bit to bring back some of the inner detail. Watch as I do that. The filaments really start to show. See that? So there is that tiny white star right there is the pulsar. Thousands of light years away, and we're seeing a star the size of Manhattan Island. It's what, 26-mile diameter or so.
Ronald asked the question, we still have no idea what type of star it was.
Well, based on the chemical composition, we can hazard a guess. And the fact is, since it went supernova, we know it was above a certain mass. So at the very least, and based on the volume and the expansion rate, we can probably figure out a lot of other details about it. In fact, those have probably already been figured out. But it most likely was going to be this star that blew up was probably a O star originally, maybe a B star, but it depends what's in the spectrum of this. If there's a lot of spectral components that indicate they're very, very heavy elements, then it had to be a massive star in order to make those elements in nucleosynthesis. So we don't really know. And the star, there's a name for the star. It's called a progenitor. The star that caused it, a progenitor star. So that's what we're looking for, is what was the progenitor star for the Crab Nebula. Ah, they're really pretty, isn't it? It's getting better.
It is.
This is the first time we have seen the Crab Nebula in a year.
Uh-huh. They call it a pulsar wind nebula.
Yeah, that's what I see. That was just kind of weird. I'm trying to find out.
Parsons.
Yeah, Earl of Ross.
He named it.
I'm trying to see what the progenitor star might have been if they did any studies on that.
Yeah, I'm looking too. That was back when he only had a 36-inch telescope.
Mm-hmm. Actually, there's 2 stars in the Crab Nebula.
I've heard that.
Yeah. Yeah. So it was probably I wonder if it was a binary star that didn't do a Type 1a supernova, which we associate with white dwarfs. Here we go. Let's find out. So it could have been it's the thing, okay. It could have been if it was a Type 1a star, Type 1a supernova, it would have meant that there was a white dwarf that exploded. But if there's 2 stars there, then that doesn't sound right. It could have been core collapse. Which means that one of the stars' core collapsed and went supernova of the 2. Now the question is, and it's a good question that people ask, would the star actually, there's a lot of research that's been done on the Crab, would that progenitor star's supernova status actually destroy the other star that it was orbiting with as a binary? And the answer is yes and no. Maybe so, maybe not. The other star could have had some of its outer atmosphere stripped, and depends how close they were. But it doesn't mean that the star would have been utterly destroyed. It would have meant it would have continued on, and maybe that's why it's a source of X-rays or gamma rays. It's there's dual sources coming from this nebula. So
says at one point, estimates of the total mass of the nebula are important for estimating the mass of the supernova's progenitor star.
Now the mass is a problem though with the Crab, if I recall.
The amount of matter contained in the Crab Nebula's filaments is estimated to be 4.6 plus or minus 1.8 solar masses. So might that be closer to a B than to an O star?
Possibly, but if it's a binary, then all bets are off.
Yeah.
But it looks, again, based on everything we're seeing, remember what I talked about, if you're seeing 2 stars in there, it means 2 stars survived, which means it wasn't a Type 1a supernova where you have a white dwarf and another red giant, and the red giant ends up feeding gas onto the surface of the white dwarf, making it go past that special mass limit called the Chandrasekhar limit, and that white dwarf would have exploded in the supernova. And that didn't happen here, because if it did, then there would be no second star here. But we have 2 stars in this nebula core. So it means that this was a core collapse supernova. It means that the progenitor star had simply run out of hydrogen and crashed. Its core collapsed and crashed in. The rebound obliterated the star. And then the companion was affected in such a way that it started to generate either gamma rays, probably X-rays, as well. So again, there's 2 sources of radiation coming from this star's pair in there. So I think that.
Yeah, I see. Did you make it down to the progenitor star section?
I did not. There is What's it say? I've looked at the crab many times and looked at the research, so I'm going from memory, so you'll have to correct me if I'm wrong about that. But
says it must have formed in a core collapse supernova.
all right, which makes sense. I mean, if you're going to have a pair of stars in there now, then it had to be core collapse if it was originally a binary star system. You know.
They do still say there's 2 stars there.
Okay.
Now
that pulsar is one of them, so that's the core collapse resultant.
The star that exploded produced a crab must have had a mass between 9 and 11 solar masses.
Okay. Yeah.
While a star heavier than 12 solar masses would have produced a nebula with a different chemical composition from that observed in the crab.
Yep, that's true. Okay, and that's what I was talking about with based on earlier. I said based on the composition of the nebula, we know what kind of progenitor star it might have been. Because I remember I said that certain elements are made only in the more massive stars, and based on that scale of what was made in the nebula, we can kind of estimate what type of star it was before it blew up.
It says it could have been blah blah an electron capture supernova.
Okay.
Which is news to me.
Well, it's still a core collapse supernova.
Yeah.
All right. Well, we've done 29. We're going to do the 30th one and stop here. So this is beautiful. Even though it's low, we've captured some nice data here. This is beautiful. Okay, I've got Messier 1 there. Okay, Crab Nebula. We're going to save that. Save it exactly as seen. Well, there we go. That's the Crab Nebula for the first time this season. That's not bad.
Yeah.
And we're actually at 145% of the scale of our sensor. So here is the size, the native size of the sensor right here. This is 100%. So that's the size it wants to be when you put it to 100%. If you try to fit everything on the page, then you get this. Okay, so you see this tiny little thing out of 2 degrees by 1.5. Not bad. Wow.
That's a good one to wrap the evening with.
I know, right?
Yeah.
So you guys,
showing us.
yeah, that's a wonderful excursion into Taurus, between the horns. See that? Between the horns. That's where we went, guys. Between the horns tonight.
Ask a favor.
Yeah.
Just one more. I doubt we'll see much, but
What do you want to see?
Mars.
Oh, it's right above. Why not?
Yes, I know.
We'll see what we can do. We are focused. We'll just head a little north and a little bit west.
Steve, I closed the page. Sorry.
There's Mars. Now I have to reduce the values and everything so we can see it. Steve asked, do you know how fast this nebula is moving through space? Well, over 100 years we noticed some movement in it. And there are studies which talk about the motion of the gases outward from the supernova. I think that we could probably research that for you and get that information. Just come back next time. It's nice to see you, Steve. Thanks for coming.
Mars is bright. It's got halos inside halos inside
I know.
halos.
That's the welcome to the F2 system. Now, because we're so small, we're going to end up having to really drop down our exposure time and our gain. So I'm going to bring the gain down first. We're going to come down from 400 all the way to 0. As you see, it's still too bright, right? So we gotta bring down. We have to bring down our exposure. That's 500 milliseconds. Let's zoom in, okay? So actually we can. Now we can look for Phobos and Deimos, maybe. All right. So let's take this down now a notch. Let's go to 100 milliseconds. That's the wrong one.
Yeah, I don't think we're going to see anything. It's only about 15 or 16 arc seconds across right now. It's only going to get up to 17 some odd arc seconds.
Yeah. I do want to see the disk. Let's do 5 milliseconds.
When we were looking at Mars, you remember 2 years ago, a little over 2 years ago.
Yeah.
Was that with this scope at F8 or the scope in Eastern in SkyTour East?
It might have been SkyTour East that we looked at it with.
Yeah. That almost looks like something right there.
Look at Daryl. They're not going to see anything. Wait, that almost looks like something. It's definitely. I definitely see surface detail. Look at looks like the polar hood.
Uh-huh.
Yeah, it looks like we got some dark detail. Notice the pixels in there.
Barely.
So we're definitely yeah, that's that by zooming in so far, which is 661%. Obviously, we are in Pixel City here.
Yeah.
This reminds me of the Hubble shots of Pluto.
Yeah. Okay. Well,
that looks
thank
good,
you for
though.
trying.
I mean, look at you can see the hood. You can see some modeling on the surface.
Yeah.
If we had a higher focal length system, we would be all right, man. Let me tell you.
Yep.
I would love to do that. We'll do that with the next telescope, though.
Okay.
Yep.
All righty. Well, are we going to call it a night? We're almost 5 hours now.
I know it. And we are. And everybody knows that music. That's what it means. You again have reached the end of a marvelous SkyTour live stream. Thank you so much for coming out and hanging out with Daryl and I as we scour the universe for all the most amazing phenomena to view and bring them to you live. So let's spend the night sleeping. And I don't think we'll see you tomorrow. Maybe if I have the urge, I'll stream. But if I don't, let's all say happy Thanksgiving to you guys and have a good holiday. So,
Gobble.
what's that?
Gobble, gobble.
Yeah, gobble, gobble. That's right. All right, guys. Have a good night. And we will talk to you again on the other side. Good night, everybody.
Good night.